Hello there, and welcome to Science for Sleep, where curiosity drifts slowly into comfort, and science becomes a soft companion to your thoughts. Tonight's quiet journey begins not with a ticking clock, but with the question of what came before the first tick ever existed. How did time begin? How did the thing that allows everything else to happen come into being? If time has a starting point, then what was before it? Or does the word before even make sense when time itself hadn't yet started keeping score? I wonder where you are listening from tonight. Maybe it's late evening where you are, the air still, the lights low, the world winding down. Maybe you can hear the sound of a distant street or the hum of your own breath in the quiet. If you find comfort in these late-night wanderings through the mysteries of the universe, I'd be grateful if you liked the video or subscribed. It helps others find their way here too, to this calm corner where wonder doesn't demand urgency. Now, let's settle in together. You don't need to picture anything complicated. Just imagine the simplest possible thing. Nothing at all. No light, no space, no sound, no clock, no ticking seconds, no before or after. The complete absence of everything, even the absence of time itself. That's the strange stage our question begins on. The human mind isn't designed to truly understand nothing. Even when we try, our thoughts sneak in a little something. A dark space, a void, a silent expanse. But those ideas already include time because you imagine the darkness existing for some duration. A moment of nothing, followed by another moment of nothing. That's still time passing. So what does it mean for there to be no time at all? No passing, no change, no duration, just absence. The question sounds simple, but it instantly pulls the ground out from under thought itself. Because to even ask, what happened before time began, is to use the word before, and before only makes sense inside time. It's like asking what's north of the North Pole. The concept doesn't apply, and yet we ask anyway. Because that's what we do. We ask impossible things and try to give them shape. Scientists have tried to trace time back to its very first measurable instant. Not the first second, or even the first fraction of a second, but as close as physics can reach toward what's called the Planck time, a number so small it barely fits into words. It's roughly 1/10,000,000 trillion trillionth of a second after the Big Bang. In that unimaginably tiny instant, the universe as we understand it began to behave in a way that physics can describe. Before that, our equations fail us. The numbers break, the rules stop working, and reality itself becomes uncertain. So what happened at that moment? Or just before it? There's no clear answer, but there are clues. Physicists have found that when they try to combine quantum mechanics, the physics of the very small, with general relativity, the physics of the very large, time starts to behave strangely. At the smallest scales of existence, time doesn't flow smoothly like we experience it. It flickers. It might even disappear, replaced by something else. A network of relationships, probabilities, quantum states that don't yet form a sequence. In that sense, time might not be fundamental. It could be an emergent property, something that appears only when enough structure forms for before and after to make sense. Imagine a film projector showing a movie. What you see on the screen is continuous motion, a story unfolding, one event leading to another. But beneath that illusion are still frames, one after another, separated by darkness. The film itself doesn't have movement until the projector starts running. Some physicists think reality might be like that. The early universe wasn't a flowing thing, but a collection of possibilities waiting for a rule set, the rule of time, to begin connecting them. But let's not run too quickly into theories. For now, let's stay near the question itself. What does it mean for something to begin? A beginning implies a change, something that wasn't, and then was. The word already contains time within it. If you were standing at the edge of creation, would there have been a moment when the clock first started ticking? Or did time arrive gradually, the way dawn brightens the sky before the sun appears? Maybe it wasn't a single event, but a slow unfolding, a transition from timelessness to temporality. Cosmologists often describe the Big Bang not as an explosion in space, but as the expansion of space itself. Space didn't appear in an empty void. The void itself grew. The distances between all points increased. And because space and time are part of the same fabric, space-time, the expansion of one meant the creation of the other. Time didn't start inside the universe. Time and the universe started together. To say the Big Bang happened 13.8 billion years ago is slightly misleading. Time itself began then, so there wasn't a before that event could be placed within. It's not that there was nothing before the Big Bang, it's that before had no meaning yet. It's a difficult thing to picture. Every instinct we have tries to put events on a timeline, a sequence. But here, the line itself was being drawn. You could think of the universe as a story that began with the first word, but there wasn't an author sitting there waiting. The act of writing and the creation of time were the same act. It's humbling to realize that even our most basic ways of thinking rely on time structure. Without it, logic, causality, even language starts to fall apart. If you imagine yourself floating outside of time, you can't move, can't think, can't wait. Those words all depend on duration. You'd simply exist as a kind of frozen awareness, though even frozen assumes a change that stopped. Maybe it's better to say you'd exist as pure being, but that too sounds suspiciously temporal. Perhaps there's no way for human thought to fully grasp timelessness. We can only circle it, like moths around a light that's not quite visible. Some scientists and philosophers have tried to find ways around the paradox. One idea is that the universe didn't begin from a single point, but rather from a quantum state where time was undefined. In this state, known as the quantum vacuum, everything that could happen existed in potential form. Then, through a random fluctuation, the kind of spontaneous event that quantum mechanics allows, that potential became actual. The universe came into being not because there was a moment when nothing turned into something, but because the conditions allowed something to be preferred over nothing. In that transition, time itself may have crystallized out, like ice forming on the surface of a still pond. Others propose that the universe has no true beginning at all. Time might loop or fold, or the Big Bang could be one of countless cycles of expansion and contraction. In that case, the beginning of time isn't a single event, but one turning point in an infinite rhythm. That idea carries its own quiet comfort. It means that the universe, in some form, has always been and will always be, not timeless, but eternally rhythmic. As you listen, notice how even thinking about time makes you feel time differently. The more we imagine its absence, the slower our own moments seem to pass. Our brains have internal clocks, patterns of neurons that pulse and reset, giving us our sense of seconds and minutes. When we focus on abstract ideas like these, those internal rhythms soften. Time feels slower, longer, more open. That's one of the gentle wonders of thinking about the cosmos. It changes not only what you know, but how you experience being here right now. If time truly began with the Big Bang, then everything that has ever happened, every star that's burned, every thought that's crossed your mind, has been part of that same expanding moment. From that first quantum fluctuation to the birth of galaxies, to the small stretch of seconds you're living through now, it's all one continuous unfolding. The beginning is still happening in a sense, because the universe is still expanding, still cooling, still carrying forward the consequences of that first burst. You are, quite literally, part of the ongoing beginning of time. This idea isn't just poetic, it's scientific. The expansion of the universe means that every clock in existence is part of the same cosmic process that started 13.8 billion years ago. Even the time it takes light to reach your eyes, the rhythm of your breathing, the slow settling of your body into rest, All of it is governed by the same unfolding of space-time that began in that first instant. You're not separate from it. You're inside it, carried along by it. It's tempting to ask what caused the Big Bang, what started it all. But that too runs into the same problem. Cause and effect require time. You can't have a cause before the beginning of time because before hasn't been invented yet. Some physicists, like Stephen Hawking, suggested that asking what happened before the Big Bang is like asking what's north of the North Pole. The question simply doesn't apply. The universe didn't emerge into time, it brought time with it. Still, our curiosity doesn't stop. We want a reason, a mechanism, a cause. Some cosmological models suggest that the Big Bang could have been a quantum event within a larger timeless multiverse, a kind of bubble forming in an endless sea of potential. In that picture, our universe's time began when our bubble formed, but outside it, in the broader multiverse, time might exist in a different or even meaningless way. There could be other bubbles, each with its own version of time, each beginning and ending according to its own internal clock. In that sense, the beginning of time is local, not universal. Time began for us, but not necessarily for everything. Even in modern physics, though, there's a strange humility that comes with these ideas. We can describe the first moments of the universe with equations and data, but the instant before that remains hidden, not by lack of effort, but by the limits of what time itself allows us to measure. The beginning of time might be forever outside our reach, because reaching requires time to pass. It's a puzzle we can think about endlessly, but never fully touch, like trying to look at your own eyes without a mirror. So here we are, in the quiet of your evening, thinking about beginnings that may not have beginnings, and clocks that might have built themselves. Somewhere, long before the first star burned, time itself found its first rhythm, and that rhythm hasn't stopped since. It's in the spin of the earth, the pulse of your heart, the slow drift of galaxies through the dark. You're moving through the same current that started when time began, or perhaps when it began to be meaningful. The seconds you feel now are ancient, not because they've lasted long, but because they belong to the same continuum that started everything. The strange comfort in all this is that even though we can't fully picture the beginning of time, we're made from it. The atoms in your body, the light in your eyes, the memories forming as you listen, all of them trace their history back through an unbroken line of causes that began at the universe's first moment of existence. You're the proof that time began, because you're living inside its flow, and the story we're about to explore continues from that very first flicker, when timelessness turned into sequence, when the universe took its first breath, and time, for the very first time, began to move. When we imagine the beginning of time, our thoughts instinctively reach for a before, but that word, simple and familiar, already pulls us into contradiction. A before implies a sequence, a change, a point of comparison. Yet in the earliest universe there was no sequence to follow, no passing of moments to count. There was, in the most literal sense possible, no time. It's almost impossible to hold this idea steady in your mind. We're creatures built to live inside time. Every thought you've ever had arrived in order, one after another. Your memories unfold like beads on a string, each one connected to what came before. Even your sense of self, that feeling of being you, depends on remembering what you were a moment ago. To picture a state where no ego exists is to ask the brain to remove the very fabric it's woven from. Still, physics demands that we try, because before time began, something extraordinary happened. Or perhaps more precisely, something happened that would later make before and after possible. If you could somehow look back to the instant before the Big Bang, you wouldn't see darkness. Darkness needs light to be absent. You wouldn't see space either, because there was no where for space to exist in. The whole concept of a location requires distances, and distance requires time, the measure of how long it takes light to cross it. Without time, there's no motion. Without motion, no separation. Without separation, no space. So what was there? Physicists have many competing ideas, but none of them resemble the intuitive pictures our minds try to draw. Some propose that the pre-Big Bang universe was a quantum vacuum, a field of pure potential where space and time were undefined. In this strange realm, energy flickers in and out of existence according to the laws of quantum mechanics. Even nothing is restless at that level. Fluctuations occur, borrowing energy from nowhere and returning it a moment later. The odd thing is that this quantum nothing isn't empty. It's full of possibility, a seething sea of uncertainty. Now, when we say before time, we must be careful. We don't mean there was a clock ticking in some other dimension, counting down to the Big Bang. There was no ticking. What we mean is that from the perspective of our universe, the one whose history we can measure, time itself hadn't yet crystallized. The quantum vacuum doesn't operate according to ordinary cause and effect. Things happen, but not in any particular order. It's a world of probabilities without sequence. The idea is so alien that even physicists struggle to describe it without using the very words it invalidates. Some models, like the Hartle-Hawking no-boundary proposal, imagine the universe as finite but unbounded. In that view, the beginning of time is like the South Pole on a globe. You can travel south until you reach it, but there's no further south beyond that. The question of what's before simply doesn't apply. The universe didn't start from a point in time. Time itself curved smoothly into existence, just as space curves around the Earth. It's an elegant way to remove the sharp edge of creation and replace it with geometry. The cosmos didn't begin abruptly. It emerged naturally, like the rounding of a corner in four-dimensional space-time. But of course, geometry isn't something we feel. Our daily sense of time is emotional, sensory, lived. We notice its flow in the way light fades in the evening, in the cooling of tea, in the quiet tick of a clock across the room. These rhythms comfort us. To imagine their absence is disorienting. Still, even in that absence, there's something fascinating. The possibility that time is not a fundamental feature of reality, but a byproduct of change. In physics, time is often treated as a coordinate, much like height or width. But some researchers believe it might be emergent, a phenomenon that arises when systems become complex enough to record differences. In a universe with nothing changing, time would be meaningless, because there'd be nothing to measure. Only when energy begins to move, when matter starts to interact, can before and after appear. In that sense, time begins whenever change begins. This idea connects closely with entropy, the measure of disorder. Entropy always increases over time, which is why time has a direction. But that means time's arrow is defined by the growth of complexity, not the other way around. If, in the earliest moments, everything was perfectly uniform with no differences anywhere, then entropy couldn't increase. Time, lacking direction, wouldn't yet exist in the way we experience it. The Big Bang, then, might not have created time so much as broken the symmetry that made time meaningful. Once differences appeared, hot and cold, dense and sparse, something and nothing, the universe gained a way to move forward. To picture this, imagine a perfectly smooth lake. No ripples, no wind, no waves. If you were suspended above it, the scene would seem eternal, unchanging. Then, a single droplet falls, sending out concentric circles. Those circles don't just disturb the surface, they define motion. Before the drop, the lake had no time in any useful sense. After it, there's a pattern. A before, a during, and an after. The drop didn't just make a splash, it created the story of a splash. Something similar may have happened at the origin of the universe. Some theories suggest that before the Big Bang, there was a state of quantum timelessness, no sequence, no ticking. Then, through an instability or fluctuation, the first difference arose, triggering expansion. In that expansion, space and time unfolded together, They weren't separate. They were two sides of one growing fabric. Every meter of distance carried with it a second of duration. The faster space expanded, the faster time itself stretched into being. That's why cosmologists often speak not of what exploded in the Big Bang, but of what expanded. The universe didn't erupt into something. It became something by expanding. It's a subtle but profound distinction. The Big Bang wasn't an event in time. It was the event that made time possible. To ask what happened before it is to step outside the frame of the question. There wasn't a before to compare it to. It's like asking what the colour blue smells like. The concepts don't intersect. Still, the human mind resists such abstractions. We crave beginnings. We want to imagine a spark, a switch, a first breath. Religious and mythological traditions often fill this gap with creation stories. Moments when a god or cosmic force speaks, breathes, or dreams the universe into existence. And while physics deals in equations rather than metaphors, the impulse behind both is the same: to understand how nothing became something and how stillness became change. If you listen closely to your own mind right now, you might notice that your thoughts arrive one at a time. You can't think two separate ideas in exactly the same instant. That rhythm, one, then another, is your personal echo of time structure. It's what allows you to build a sentence, follow a melody, or remember what was just said. In that way, you're a microcosm of the universe itself, a being whose very existence depends on time unfolding. But what would it mean to exist without that unfolding? If the earliest universe was truly timeless, then nothing could happen in it, because happen implies sequence. So how did we get from a timeless state to a temporal one? One possible answer lies in quantum decoherence, the process by which quantum systems transition from superpositions to definite states. In the timeless quantum vacuum, everything that could exist does so in overlapping probability waves. When enough energy or structure accumulates, those possibilities interfere with each other, collapsing into a specific configuration. That collapse, in a sense, defines an order. The first moment might simply be the first collapse, the first definite state. From then on, change became possible, and with it, time. Another idea, proposed by physicists like Carlo Rovelli, suggests that time is not universal but relational. It doesn't exist independently. It's a measure of change between systems. If nothing changes, there's no time. If everything changes together, time still has no meaning. Only when one part of the universe changes relative to another can we say that time has passed. This means that before the universe had enough internal diversity, before it had matter, motion, temperature differences, there was nothing for time to compare. The universe was a single, unified state. Time was waiting for relationships to form. That word, waiting, is misleading, of course, because it implies duration. But it's difficult to speak of timelessness without borrowing from time's vocabulary. Our language was built inside the flow of moments, so every sentence we form carries that current within it. Even the phrase, "when there was no time," smuggles time in through the back door. The best we can do is use analogy to hint, gesture, and approximate. Imagine standing beside a frozen river. Beneath the ice, the water is still there, full of potential motion. All it needs is warmth to flow again. In the timeless quantum state, reality might have been like that, frozen in perfect symmetry. Then something shifted, a fluctuation so small it can't even be described in terms of seconds, and the ice began to melt. Motion appeared, flow began, and with that flow, time found its direction. If we could somehow replay that moment, the universe's birth wouldn't look like an explosion. It would look like a transition, from stasis to evolution, from potential to unfolding. A kind of awakening, not in a spiritual sense, but in a physical one. The universe didn't appear all at once. It began to happen. That happening is still going on. Every second that passes now is a continuation of that first unfolding. This way of seeing things also changes how we think about beginnings in general. In our lives, we often picture beginnings as sharp points. The first day of a job, the first step on a journey, the first word of a story. But most beginnings are actually transitions. They don't start from nothing. They grow from conditions that were already forming quietly, almost invisibly. The birth of time might have been the same, not a bang but a bloom, not a sudden command but a gradual emergence. It's possible that the universe, before it became our universe, existed in a state where the distinction between time and space didn't even exist. Some quantum gravity models describe such a phase as Euclidean, meaning all dimensions were spatial. Time hadn't yet differentiated itself as something special. Only when the universe expanded and cooled did one dimension take on a temporal character, the one we now call time. You could say that time began when the universe decided to start moving forward instead of simply existing in all directions at once. Every attempt to describe this moment carries uncertainty. We're working at the limits of knowledge, where equations stretch to breaking and metaphors strain to keep up. But even that uncertainty is part of the beauty. It reminds us that we live inside something far larger than understanding, and yet we can still trace its echoes in the glow of distant galaxies and the whisper of cosmic background radiation. Those faint signals, still travelling across the universe, are the fossil light of time's first moments. Proof that whatever timelessness once was, it didn't last. Change began, and once it began, it never stopped. If you think about it, every night when you close your eyes, you perform a small reenactment of that transition. Sleep erases your awareness of time. Hours pass, but you don't feel them. Then, when you wake, time returns. The light outside tells your body it's morning again, and you begin counting the day without realizing it. In a way, each awakening is your own private Big Bang, the return of time to consciousness. The universe did something similar, but on a scale beyond imagining. And as you lie here listening, you're participating in that same unfolding. The molecules that make up your body were forged in stars, which formed from clouds of hydrogen born in the first minutes after time began. Your heartbeat marks the rhythm of an ancient process, energy moving, entropy increasing, moments stacking quietly into history. When there was no time, there was no heartbeat, no thought, no change, but once the flow began, everything became possible. The beginning of time wasn't just the start of the universe, it was the start of every potential that would ever follow, including this moment now, the one you're living through, as you listen to the story of how moments themselves first came to be, and as the universe kept expanding, as energy cooled and structure began to form, time became smoother, more predictable, more measurable. The chaos began to find its rhythm, and what was once impossible to imagine, a world where events could unfold one after another, became reality. The timelessness that once defined existence gave way to a universe where clocks could tick, stars could burn, and thoughts could arise. The river had begun to flow, and everything we know was carried with it downstream into the great unfolding of history that still continues tonight. From that silent state where time had only just begun to make sense, the universe expanded with astonishing speed. It didn't move into space. Space itself was what was moving. Every direction stretched away from every other, and in that expansion, time began to unfold like the first slow breath after a long, suspended pause. This was the universe's first inhale, a single cosmic motion that would carry everything that would ever exist within it. If you could somehow stand within those first moments, though standing wouldn't mean anything yet, you wouldn't see a vast explosion. There wouldn't be a centre or an edge, no roaring fireball spreading through empty darkness. Instead, the entire fabric of reality itself would be swelling uniformly, an everywhere expansion. Every point in existence would be moving away from every other point, not through space, but as space. The distances between all points were increasing, and with that increase came time's steady heartbeat. Physicists sometimes call these first instants the Planck era. It lasted for about 10 to 43 seconds, a time span so small that the human brain can't picture it. Within that incomprehensible slice of duration, the laws of physics as we know them didn't yet operate. Gravity, electromagnetism, and the nuclear forces that hold matter together were not yet distinct. They were woven together in one unified field. What that state looked like, no one knows. Our equations collapse when we try to probe it. But what's certain is that the seeds of everything, energy, matter, motion, even time, were contained within it, waiting to separate and interact. As the universe expanded, it cooled. That cooling is crucial. Temperature isn't just about heat, it's about energy and how freely it moves. When the universe was unimaginably hot, everything existed as pure energy, a chaotic blur without boundaries. As it cooled just enough, the first physical laws began to emerge. Gravity began to separate from the other forces, shaping the structure of time and space itself. The smooth symmetry of the early universe broke, and in that breaking, reality gained definition. This process didn't happen in one clear instant. It was more like a slow unblending, a kind of cosmic differentiation. Imagine heating a piece of metal until it glows white hot. In that state, it's uniform, no part is different from any other. But as it cools, layers form, crystals align, structure appears. The universe did something similar, though on scales and energies that defy comprehension. It went from pure, structureless energy to a system of interacting fields, a stage where particles could form, time could advance, and cause could lead to effect. By the time the universe was a trillionth of a second old, it was already unimaginably large compared to what it had been at its birth. During a phase called cosmic inflation, the expansion rate skyrocketed, space ballooned exponentially, doubling in size many times over in less than an eye blink. This sudden growth smoothed out irregularities and gave the universe its evenness, a balance we can still see today in the cosmic microwave background radiation, the faint afterglow that fills all of space. Inflation is one of the most powerful ideas in modern cosmology. It suggests that tiny quantum fluctuations, those random ripples of energy that occur even in a vacuum, were stretched to cosmic scales. The minute differences in energy density became the seeds of galaxies, stars, and planets billions of years later. What began as subatomic noise became the architecture of the cosmos. That means the galaxies we see in the night sky are, in a way, magnified echoes of quantum vibrations that existed in the universe's first fractions of a second. The small became vast. The uncertain became real. During those first fleeting instants, the universe was dense beyond imagination. Not dense like a star or a planet, but dense like all the energy of everything that will ever exist compressed into a space smaller than an atom. The pressure, temperature, and energy levels were extreme, yet perfectly balanced to allow expansion instead of collapse. If the rate of expansion had been even a fraction different, a few parts in 100 trillion, the universe would either have recollapsed instantly or expanded too quickly for matter to ever form. The fact that we exist at all is evidence that the early universe found a delicate balance between chaos and stability. As the expansion continued, something remarkable happened. Time began to take on a more familiar shape. Once energy and matter could interact consistently, the universe had a framework for cause and effect. Events could unfold in a sequence, and that sequence could be measured. The clock of the cosmos had started ticking not metaphorically, but literally. About 1/10,000th of a second after the beginning, the universe cooled enough for quarks, the fundamental building blocks of matter, to form. Quarks combined in groups of 3 to make protons and neutrons, the particles that would later build atoms. But at this stage, it was far too hot for atoms to exist. The entire universe was a glowing plasma, a storm of particles colliding at near light speed. In this turbulent sea, energy was constantly transforming into matter and back again. Einstein's famous equation, E mc2, wasn't just a concept here, it was the reality of every instant. The formation of these first particles marked an important transition. Matter and energy were no longer indistinguishable. The universe had begun to store information, to create persistent structures. You could almost say that time began to accumulate memory. Each interaction, each collision, each formation left behind traces in the form of conditions that would affect the next. In that way, the universe was writing its own history for the first time. A few seconds later, something new appeared. Light. As particles collided and decayed, they released photons, the first radiation. But that light couldn't travel far. The universe was still opaque, too dense for photons to move freely. It would remain that way for hundreds of thousands of years. Still, the mere existence of light marked a turning point. Energy could now spread in waves instead of only as collisions. The flow of time began to smooth out, becoming less chaotic, more ordered. When we call this period the first seconds, it's worth remembering how long a second feels to us. We can count 1 Mississippi, 2 Mississippi. But these early seconds contained everything. All the potential, all the energy, all the structure of what would become stars, planets, and life itself. Those seconds were the most important in cosmic history. They were the first pulse of everything. Around 1 minute after the beginning, the universe cooled enough for protons and neutrons to bind together, forming the first atomic nuclei. This process is called nucleosynthesis. In that brief window of time, hydrogen and helium, the two simplest elements, were created. Almost all of the hydrogen in your body, in the water you drink and the air you breathe, was made then. The helium that fills balloons and stars alike was born in those same minutes. Every heavier element, from carbon to iron to gold, would have to wait billions of years to form in the hearts of stars. But the foundation of chemistry, and therefore of life, was laid in that first minute. Even at this early stage, time had meaning. Processes took measurable durations. Reactions had rates. The universe was no longer timeless chaos. It was governed by predictable laws. Those laws didn't come from outside. They emerged from within, from the way energy and space behaved together. It's easy to forget how astonishing that is. There was no external clockmaker setting the rules. The rules arose naturally, and once they did, they remained constant enough for everything else to follow. As the universe continued to expand, its density dropped, and its temperature kept falling. After about 300,000 years, it finally cooled enough for electrons to combine with nuclei, forming neutral atoms. This event is known as recombination. For the first time, light could travel freely. The universe became transparent. The radiation released then has been travelling ever since, stretching with the expansion of space. We can still detect it today as the cosmic microwave background, the faint afterglow of the universe's first visible light. When scientists map that radiation, they are literally looking at the moment when light first separated from matter, when the universe went from opaque to luminous. That faint radiation, spread across the sky, tells us not only how the universe looked back then, but how time itself was structured. The patterns we see in it, tiny fluctuations in temperature and density, correspond to the earliest ripples in spacetime. They are the echoes of the first physical seconds, and remarkably they show us that the universe, even in its infancy, was almost perfectly uniform, differing only by a few parts in 100,000. Those tiny irregularities were enough to give gravity something to work with, eventually pulling matter together into stars and galaxies. So when we look at that faint cosmic light, we're not just seeing the early universe, we're seeing the first chapters of time written into the sky itself. Every photon from that era has been travelling for nearly 14 billion years, carrying information about those first seconds. When they reach our telescopes, they are messengers from a time when time was still learning to flow. If you think of the universe as a vast story, this was its first paragraph, dense, brief, but containing every theme that would unfold later. Expansion, structure, interaction, decay, rebirth. It all began here, and unlike a human story, it didn't need a storyteller. The rules of physics were enough. Energy followed patterns, and those patterns gave rise to everything else. There's a strange humility in realizing that time, which feels so personal to us, began as a property of the cosmos itself. The second on your wristwatch is a descendant of those early moments. When your heart beats, it does so according to biological rhythms shaped by light and energy that trace back to that first expansion. The very concept of duration, that one thing can follow another, owes its existence to that single cosmic breath. Every galaxy, every star, every atom is a record of that unfolding. You, sitting or lying here now, are made of matter that was once compressed into that first tiny universe. The calcium in your bones, the iron in your blood, the carbon that builds your cells, all of it owes its existence to processes that began when the universe was less than a minute old. You are a living continuation of the Big Bang, an ongoing expression of that first expansion, breathing still, thinking still inside the same flow of time. And even now, billions of years later, the universe hasn't stopped expanding. Space continues to stretch. Galaxies drift farther apart, and time itself keeps accumulating new history. That first cosmic breath has never ended. It's still unfolding, still carrying us forward. Every moment we experience is part of the same expansion that began back then. The Big Bang wasn't a one-time event. It was the start of a process that has never paused. The air you're breathing right now contains atoms that were part of that first moment, stretched and cooled, passed through stars, planets, oceans, and now through you. Time, for all its vastness, connects directly to this instant, to the warmth in your body, the rhythm of your breath, the flicker of awareness that you call the present. The universe began with one continuous movement, and that movement never stopped. It's still happening now, in every particle, in every second that slips quietly by. And somewhere, perhaps beyond what we can yet measure, that first breath continues to expand into what lies ahead. Not an ending, but the endless continuation of the moment when time began to flow. When scientists talk about the beginning of the universe, they often start with a phrase that sounds deceptively simple. Something came from nothing. It's one of those ideas that sounds profound until you try to picture it. Because what is nothing really? When we close our eyes and imagine it, we tend to think of empty space, a dark void stretching endlessly. But that isn't nothing. That's already something. It has dimension, volume, potential, and silence. True nothingness isn't black or empty or still. It isn't anything at all. It has no space, no time, no properties. It doesn't exist. Which makes the idea of something emerging from it almost impossible to describe. And yet, that's where the story seems to begin. To understand how something can arise from nothing, we have to start by questioning what nothing means in the language of physics. In science, nothing isn't the absolute void of philosophy. It's more like a quantum vacuum, a state with no matter, no radiation, but still full of underlying energy. Even in what seems like empty space, quantum fields hum quietly. They fluctuate spontaneously, producing pairs of particles and antiparticles that appear and vanish almost instantly. These fleeting events happen everywhere, all the time, even now. They're the reason that perfect emptiness doesn't really exist. The universe, at its most fundamental level, is restless. If you could somehow zoom in to the smallest possible scales, far smaller than atoms or even protons, you'd find that the so-called vacuum isn't smooth or silent. It's a jittery landscape of probabilities, where virtual particles flicker into existence and disappear before they can be measured. These fluctuations are permitted by the uncertainty principle, one of the core ideas in quantum mechanics. It says that certain pairs of properties like energy and time can't both be precisely known. If you allow a brief enough window, energy can spontaneously appear as long as it vanishes quickly enough to balance out. Over vast scales, these tiny fluctuations can accumulate. So, in that sense, nothing might never have been perfectly nothing. Even the absence of matter may have contained the seeds of potential, a kind of raw quantum possibility waiting to be stirred. Some cosmologists suggest that the entire universe could have arisen from such a fluctuation. In that scenario, the total energy of the universe might actually be zero. The positive energy of matter could be balanced by the negative energy of gravity. If those two sums cancel each other perfectly, then the universe could, in principle, emerge without violating any laws of physics. It's an idea that sounds abstract, but it's mathematically consistent. The universe may have cost nothing to create. This doesn't mean it appeared out of a magician's hat. It means that the boundary between nothing and something may not be as clear-cut as we think. The laws of physics might allow energy, space, and time to arise from a state where they're not yet defined, like ripples forming on a perfectly still surface. When those ripples appear, the surface hasn't changed in essence. It's still the same field, but its state has shifted. Something similar could have happened to the quantum vacuum that preceded the universe. A fluctuation reached a critical point, and the universe began expanding. But this explanation only pushes the question back a step. If the universe emerged from quantum laws, where did those laws come from? Why was there a vacuum at all? Why not absolute nothing? Not even the potential for fluctuation? These are the questions where science edges up against philosophy, and where language starts to break apart. Some physicists suggest that the laws of physics themselves may be inevitable, that they represent the only consistent way for reality to exist. Others propose that our universe is just one of many, each with its own version of physics, born from a deeper, timeless reality that we can't access directly. Still, even these ideas rely on a kind of meta-something, a framework that exists even when we try to talk about nothing. That's the challenge. Our minds evolve to think in terms of cause and effect, presence and absence, before and after. To describe true nothingness, the absence of any context at all, is beyond what our brains can handle. The moment we imagine it, we've already created something, the act of imagining. And yet the notion that the universe began from nothing isn't as absurd as it might seem. In fact, traces of that beginning are still all around us. The cosmic background radiation, the faint afterglow of the Big Bang, shows that the universe started in a state of extraordinary uniformity. Every direction looks almost the same, as if everything began from a single, simple condition, one that was incredibly close to nothing. From that near nothingness, complexity slowly arose. To get a sense of how that can happen, think about a snowflake. Each one starts from a single molecule of water vapor, floating in a cloud. As it cools, it attracts more molecules, arranging them into patterns. The final crystal looks intricate, delicate, and deliberate. But it isn't designed by anything. Its complexity arises naturally from simple physical rules. The same principle applies on the cosmic scale. Given the right conditions, structure emerges spontaneously. Order grows out of uniformity. Something intricate can come from almost nothing, provided the laws of physics allow it. There's another layer to the mystery. According to relativity, space and time are intertwined. You can't have one without the other. That means if time began at the Big Bang, so did space. The universe didn't expand into a pre-existing void. The expansion created the void itself. When cosmologists say the universe is expanding, they don't mean it's pushing outward into nothingness. They mean that space itself is stretching, carrying galaxies along with it. The distances between everything are increasing, but there's no edge, no boundary, and no outside. If you could somehow travel far enough, you wouldn't find a wall or a border beyond which there's nothing. You just keep looping through expanding space. The concept of beyond doesn't apply because space itself defines what beyond means. This makes the question, what did the universe expand into, meaningless in the same way what's north of the North Pole is meaningless. The coordinates simply stop making sense. In that light, nothing might not be an external emptiness at all, but the absence of space-time itself, a condition that can't even be pictured. When the Big Bang occurred, it didn't burst into nothing. It transformed nothing into something, redefining what existence could mean. For some physicists, this transformation has a mathematical basis. The equations of quantum cosmology describe a state known as tunneling from nothing. It's based on a concept from quantum mechanics where particles can move through energy barriers they shouldn't be able to cross, thanks to uncertainty. Applied on a cosmic scale, this means the universe could have tunneled into existence from a state with no time, no space, and no matter. The probability of that happening is unimaginably small, but given infinite potential, even an event with vanishingly small probability can eventually occur. In that sense, the universe didn't need a cause. It was inevitable, not because it was planned, but because in a timeless realm of pure possibility, something was bound to happen. It's a dizzying concept that our entire reality could be the result of a quantum event in a realm where event has no real meaning. Yet, there's an odd logic to it. If nothing truly existed, there would be no reason for it to stay that way. Nothingness, by definition, has no laws, no restrictions, no structure to prevent change. Paradoxically, that means it's unstable. Even the tiniest fluctuation, if such a thing could occur, would create a difference. And with difference comes time, space, and energy. In that view, nothing is like a perfectly balanced pencil standing on its point, so delicately poised that even the smallest perturbation causes it to fall, creating motion where there was stillness. From that first imbalance, the universe may have been born. Energy condensed into particles, space stretched, and time began to flow. The first something, whatever form it took, immediately began to change because that's what energy does. It moves, it interacts, it evolves. Once change began, there was no going back. Nothingness had been replaced by a self-sustaining process, an expanding, cooling, ever-transforming cosmos. And within that expansion, structure began to emerge naturally. Quantum fluctuations created tiny differences in density. Gravity amplified those differences, pulling matter together in some places while leaving others emptier. Over billions of years, those small variations grew into galaxies, stars, and planets. The same process that gave rise to the Milky Way and the solar system also governs the growth of clouds, the ripples on water, and even the clustering of neurons in your brain. It's the universal tendency of energy and matter to organize themselves when given the freedom to move. What's remarkable is how stable that something became. The physical constants of our universe, the strength of gravity, the charge of the electron, the speed of light, are finely balanced. If any one of them were even slightly different, stars might never have formed, chemistry might not exist, and life would be impossible. Some see this as evidence of fine-tuning, others as a selection effect. In a multiverse with countless variations, only the universes with stable conditions could develop observers capable of noticing them. Either way, it means that our particular something, this universe, this version of reality, occupies a narrow, precious range between chaos and collapse. But even if we can describe the steps from nothing to something, the deeper question remains: why is there something instead of nothing at all? Why do the laws of physics exist? Why do quantum fields fluctuate? Why is there potential instead of absolute absence? These questions stretch beyond the reach of current science. They live at the border between physics and philosophy, where even the best equations can only gesture. Some thinkers propose that nothing may simply be impossible. That existence in some form is the default state. Just as zero isn't the absence of numbers but a position on a number line, nothingness might be part of the larger spectrum of being. In that case, the universe didn't come from nothing. It came from a deeper kind of reality where something and nothing are two sides of the same coin. When one flips into the other, time begins. The transition from nothing to something might not have been a one-time event either. In some cosmological models, universes can give rise to other universes through quantum processes, black hole formation, or cosmic inflation that never fully ends. In those scenarios, creation is ongoing. Every moment, somewhere beyond our horizon, new spacetimes may be blooming into existence, each with its own version of something. The idea that nothing could have been stable seems less likely when reality appears to favour abundance, an endless branching of existence, each one tracing its roots back to the instability of nothingness itself. And so, when we talk about how time began, we're really talking about how something, any something, became possible. Before time, there was no order, no before or after, no cause or consequence. The instant something existed, even if it was only the faintest shimmer of quantum energy, difference appeared. And that difference is the essence of time. The first something didn't just break the silence, it created the rhythm. The evidence of that transition is still embedded in the world around you. The warmth of sunlight, the atoms in your body, the expansion of space, all of it traces back to that first moment when potential became actual. Every sound, every motion, every thought is part of the same continuous story that began when nothing became something and hasn't stopped since. The next time you look at the night sky, remember that what you see isn't just a collection of stars scattered in darkness. It's the visible record of that ancient transformation. The light that reaches you has travelled for billions of years through a universe that began as less than nothing and became everything. You're made of that transition, built from the matter that arose when time first learned to move. The atoms in your eyes were once part of that early energy. The breath you take now is an echo of the universe's first expansion, the same exhalation that turned emptiness into existence. And as that breath continues, as space stretches and galaxies drift, we are still inside that first unfolding. Nothingness hasn't returned, because once time began, there was no going back. Change sustains itself. Existence persists. And somewhere in that persistence lies the quiet wonder that out of what we cannot imagine, out of nothing at all, everything you've ever known was born and continues to become. As the first flicker of something began to expand and cool, what emerged wasn't merely matter or energy, but the very fabric that would define how both could exist. Space and time, inseparable and interwoven, came into being together. It's one of the most profound truths that modern physics has uncovered, that you cannot have space without time, nor time without space. They are two sides of the same continuous fabric, a single entity known as spacetime, and their birth marked the beginning of everything that would ever happen, everywhere that anything could ever be. When Einstein first described this union in his theory of relativity, he changed the way we think about the universe forever. Before him, space had been seen as a static stage, an empty arena where events unfold, while time ticked uniformly in the background. But Einstein showed that the two are connected so deeply that neither exists independently. Matter and energy curve space-time, and that curvature tells matter how to move. Time doesn't flow at the same rate everywhere. It bends, stretches, and slows in response to gravity and motion. The clock that beats on a mountaintop ticks slightly faster than one in a valley, and one near a massive star ticks slower still. That means time itself is part of the structure of the universe, not something apart from it. To understand how space and time were born, imagine the universe as a kind of growing fabric, a smooth sheet that started as a point and began to stretch. There was no centre to this expansion, no edge, no outside. Every point on the sheet was moving away from every other point, and as it did, new space was being created between them. That expansion is still happening today, though at a pace that seems gentle compared to the furious inflation of those first moments. When we look deep into the night sky, we're looking across billions of light years of stretched space-time, seeing the light from galaxies that left their sources when the universe was young. But before space-time began stretching, there was no before in any meaningful sense. That's what makes the birth of time so strange. We are so accustomed to thinking in terms of sequences, first this, then that it's almost impossible to picture an existence where sequence doesn't apply. In the earliest instant, the universe wasn't yet a story unfolding. It was the possibility of a story. Only when space-time began to form did there appear a way to tell it. The creation of space-time is tied to symmetry breaking, the process by which the fundamental forces of nature separated from one another. In the beginning, all the forces were one. Gravity, electromagnetism, and the nuclear forces existed in perfect unity. As the universe expanded and cooled, that symmetry broke. Gravity was the first to step apart, defining the shape of space-time itself. The moment gravity became distinct, time gained direction. From that point onward, change could accumulate. The flow of moments began. To see why gravity plays this role, consider how it affects time even now. A clock near a massive object runs more slowly than one far away. That's not because the clock itself is malfunctioning, it's because the structure of space-time is curved by mass. In a sense, massive objects warp the very fabric through which time flows, stretching it so that seconds lengthen in their presence. When the universe was dense beyond comprehension, those curvatures were extreme. Time, if it could be said to exist, would have been stretched and compressed in ways that defy intuition. As expansion reduced that density, space-time smoothed out, and time began to flow more evenly. There's an elegance in this idea that time began as a response to expansion. It's as if the universe needed space in order to breathe, and the act of breathing created the rhythm we call time. Without distance, there could be no movement. Without movement, no change. Without change, no time. When the first dimensions opened up, the possibility of difference appeared, and with difference came sequence. The universe could now evolve, not just exist. Even though we talk about space and time as separate things, they are in every measurable way one. You can't move through space without moving through time, and you can't move through time without it having spatial consequences. When you walk across a room, you also move forward in time. When you travel faster, time for you slows down compared to those who remain still. It's an inseparable dance. And that dance began with the first expansion of the cosmos. In the earliest fraction of a second, space-time was quantum in nature, jittery, uncertain, governed by probabilities rather than smooth geometry. Physicists call this the Planck epoch, the shortest slice of time that can have meaning according to current theories. Below that scale, the very concept of before and after breaks down. The Planck time, about 1043 seconds, represents a kind of boundary beyond which our equations can't go. It's not that there's nothing beyond it, but the time itself loses definition. You can't measure duration without clocks, and there were no clocks yet, not even in principle. The universe hadn't cooled enough to allow for stable systems that could repeat patterns. Once the expansion progressed past this quantum haze, space-time settled into something smoother and measurable. When that happened, the first physical laws began to apply consistently. Space gained geometry, time gained direction, energy could travel in waves, matter could form and move, the universe became describable, You could, in theory, have placed a clock somewhere and it would have ticked. That was the moment when the cosmos transitioned from timeless potential to temporal unfolding. This transition wasn't sudden in the way a light switch flips on. It was more like dawn, a gradual brightening of structure out of chaos. The early universe may have contained regions where space-time behaved differently, where the concept of time hadn't yet stabilized. Quantum fluctuations could have created bubbles of expanding space, some collapsing, others growing. The one that grew into our universe may simply have been the one whose conditions allowed space-time to stretch continuously, rather than tear. Out of that stability, a vast self-sustaining expansion began. The birth of space and time as we know them. When you picture this, don't imagine a center exploding outward. Instead, imagine the fabric itself stretching everywhere at once. Every part of the universe was and still is the center of expansion. This is why, no matter where you look from, galaxies seem to be moving away in all directions. There isn't a point in space you could travel to where the Big Bang happened. It happened everywhere, because everywhere was created in that moment. There's something profoundly humbling about that. It means that even where you sit now, space was born. The atoms that make up your body are assembled from material that originated in the expansion of space-time itself. The time flowing through you is part of the same unfolding that began then and has continued, unbroken, ever since. You are literally living inside the process that began at the birth of time. At that early stage, the universe didn't yet have stars or galaxies or even atoms. It was a near-perfect fluid of energy, expanding and cooling. The relationship between space and time dictated everything that followed. As space expanded, it stretched the energy within it, lowering its temperature. That cooling slowed interactions, allowing complexity to emerge. Without expansion, time might have remained undefined. But as the distances between points increased, so did the intervals between events. The geometry of space gave rhythm to the unfolding of time. Even now, the rate at which time passes is tied to the structure of space. As the universe expands, the distances between galaxies increase, and with that expansion, the flow of cosmic time continues. In the far future, as space continues to stretch, galaxies will drift so far apart that their light will no longer reach one another. Time will still flow, but the universe will grow increasingly quiet. The same expansion that gave birth to time will eventually lead to a vast stillness, not an end, but an endless continuation into greater isolation. When scientists try to describe the birth of space-time, they often turn to mathematics. Equations like Einstein's field equations or the Friedmann models describe how space expands and curves in response to energy. But beneath those equations is something more intuitive, the recognition that the universe isn't just in time, it is time. Every change, every movement, every thought is a local ripple in the fabric that began forming in those first moments. There's no external clock keeping score. The universe measures itself by its own unfolding. This makes the concept of now deeply relative. Your now is defined by the light reaching you at this moment, but that light may have travelled for billions of years. When you look at a star in the night sky, you're seeing its past, not its present. Every observation we make is delayed by the time it takes light to reach us. There is no single, universal now that applies everywhere at once. The flow of time is woven into the structure of space itself, and each point in that structure has its own timeline. The birth of time didn't create one river. It created countless streams, all flowing at slightly different speeds, all connected through the curvature of space-time. If you could somehow stand outside the universe, though that's not really possible, you wouldn't see time as we experience it. You'd see the entire history of the cosmos laid out at once, like a vast four-dimensional sculpture. The Big Bang, the birth of stars, the rise of life, and the present moment would all coexist in that structure. From that viewpoint, time doesn't flow. It simply is. The passage we feel is an illusion created by consciousness moving along its own world line within the structure. But from our perspective, inside the flow, time feels alive, continuous, and unstoppable. This duality, time as both static geometry and lived experience, is one of the most beautiful mysteries of physics. It shows how deeply intertwined we are with the universe. When you look at a clock, you're not observing something separate from yourself. You're witnessing the same cosmic rhythm that began when space and time were born. The second hand moves because electrons move, because atoms vibrate, because energy interacts according to laws that trace back to those first moments. Every tick is an echo of the expansion that began more than 13 billion years ago. And yet, that expansion wasn't random. It had structure from the very start. Quantum fluctuations in the early universe, tiny differences in density, were imprinted onto the fabric of spacetime itself. These variations became the scaffolding for everything that followed. Where the density was slightly higher, gravity would eventually pull matter together, forming galaxies. Where it was lower, space would stretch more freely, creating the voids between clusters. Those patterns were encoded in the very geometry of space and time, and they remain visible in the cosmic microwave background. When scientists map that faint radiation, they're seeing the texture of space-time as it was just after its birth, a baby picture of time itself. There's a quiet comfort in realizing that we live inside a universe whose beginnings are still visible. Every photon of cosmic background light carries a memory of those first moments. When it hits a telescope, it's a message from the time when space and time were still new, still finding their balance. That light has been travelling for nearly 14 billion years through the same space-time that once emerged from the quantum haze. We can't reach the beginning directly, but its signature reaches us continuously, gently, across the darkness. Even now, the expansion of space-time continues to define our reality. The galaxies we observe are receding, not because they're moving through space, but because space itself is stretching between them. That stretching carries time along with it. Every second that passes here corresponds to new space being created everywhere. The universe grows not only in size but in duration. The birth of space and time wasn't an isolated event long ago. It's an ongoing process. The fabric keeps unfolding, and we are woven into it. If you sit quietly and notice your breathing, the rhythm you feel, in, out, isn't so different from the rhythm of the universe. Expansion, cooling, change, renewal. The universe breathes through you. The space inside your lungs expands as the larger space outside does. The time that carries your thoughts forward is the same time that carries galaxies apart. You're not merely living in the aftermath of the Big Bang, you're part of the continuation of it. Every breath you take is drawn through the same space-time that was born when the cosmos began, and as this vast fabric continues to stretch, as it carries stars and planets and thoughts further along their trajectories, we remain small but connected participants in the same event, the ongoing birth of space and time. It hasn't stopped. It's still happening now, in the quiet between heartbeats, in the faint light travelling across the sky, in the unseen motion of galaxies drifting further into the cosmic distance. The beginning never ended. It simply became everything that followed. The earliest fraction of the universe's existence is a region we can barely describe, yet it defines everything that followed. Physicists call it the Planck moment, the first measurable instant after the birth of space-time, when the universe was so small, so hot and so dense that our current understanding of physics simply cannot describe it fully. It lasted for roughly 10 to the power of negative 43 seconds, an amount of time so short that it feels meaningless when spoken aloud. But within that span, the universe transformed from a condition beyond comprehension into one where the laws of nature could begin to operate. To imagine that scale, try to picture a second, then divide it by 1 billion, and then by another billion. and keep dividing 43 times. The number becomes absurdly tiny, beyond anything we can measure or even compare. The Planck moment represents not just a small slice of time, but the smallest slice of time that could ever make physical sense. Below that threshold, the very concept of time loses definition. At that instant, the universe was smaller than the smallest particle we can conceive of, yet it contained the energy of everything that would ever exist. Density and temperature were near infinity. Matter as we know it didn't yet exist. Neither did atoms, nor light, nor even fundamental particles. What did exist were quantum fields, vibrating entities that filled the nascent spacetime. These fields, governed by uncertainty, fluctuated chaotically, creating tiny irregularities that would later shape the entire structure of the universe. To speak of the Planck moment is to speak of a boundary. On one side, physics as we know it begins to function. On the other, the rules dissolve into mystery. Our theories of relativity and quantum mechanics, both astonishingly accurate in their domains, fail to coexist at this scale. Relativity describes the smooth curvature of space-time, while quantum mechanics describes the jittery world of subatomic particles. But at the Planck scale, space-time itself behaves quantum mechanically. It isn't smooth, it flickers, trembles, and fluctuates. Instead of a continuous fabric, it becomes a frothing sea of probabilities, where geometry itself might appear and vanish in bursts. This hypothetical structure is sometimes called quantum foam, a name that sounds playful, but describes something far from gentle. Imagine space and time boiling at unimaginable intensity, with tiny bubbles of curved space-time appearing and disappearing constantly. Each bubble could represent a different geometry, a different possible configuration of the universe. Most vanish almost instantly, but one, perhaps by chance, perhaps by inevitability, expanded rather than collapsing. That expansion became our universe. When scientists attempt to model this period, they encounter mathematical infinities, numbers that explode instead of resolving. This tells us that our equations are incomplete. We need a theory that unites general relativity and quantum mechanics into one coherent description, something often called quantum gravity. Several candidates exist, such as string theory and loop quantum gravity, each attempting to explain what spacetime looks like at the smallest scales. But none has yet been confirmed experimentally. The Planck moment remains a frontier, a place where even our most powerful ideas grow uncertain. In loop quantum gravity, for instance, spacetime isn't continuous at all. It's made up of discrete chunks, tiny, indivisible units of volume and area, woven together like the threads of an unimaginably fine fabric. Time itself in this picture moves in quanta. It doesn't flow smoothly but ticks forward in imperceptible steps, like the frames of a film played so quickly that we perceive it as motion. If this is true, then the Planck moment wasn't a single point in time, but the first frame in the film of the universe. The transition from nothing to something might have occurred not continuously, but through the first quantized leap of existence. In string theory, the approach is different. Instead of particles, it describes the universe as made of tiny vibrating strings of energy. Their vibrations determine everything: the type of particle, its mass, its charge. Time and space emerge from the way these strings interact. In that model, the Planck scale corresponds to the size of the strings themselves. Below that, there is no smaller unit to measure. The universe simply cannot be divided further. It's as though nature has set a fundamental resolution limit, a smallest possible pixel in the cosmic picture. Regardless of which model turns out to be true, the idea remains that the Planck moment marks the threshold between the timeless and the temporal, between quantum uncertainty and measurable reality. It's the instant when the universe became capable of having a history. Before it, time and space were undefined, perhaps entangled in some abstract higher dimensional state. After it, they began to behave in ways we can describe, measure, and eventually observe. It's extraordinary to think that everything that has ever existed, every star, every atom, every heartbeat, can trace its ancestry back to this almost non-existent moment. The entire cosmos, in all its vastness, was once compressed into a state smaller than anything we can measure. The density was so high that if you tried to model it, the curvature of spacetime would loop back on itself. Gravity and quantum forces were of equal strength, a condition that no longer exists anywhere in the universe today. To visualize it, imagine the entire visible universe, all the galaxies, stars, and voids, compressed into a single point smaller than an atomic nucleus. Then imagine that point flickering, not in space but as space, because there was no external location for it to occupy. It wasn't expanding into something, it was expanding as something. The distances between every possible point were increasing, defining space as they grew. During the Planck moment, the rate of expansion was beyond comprehension. The universe doubled in size countless times in an instant. This phase is what physicists later called inflation, a period of exponential growth that smoothed out irregularities and set the stage for everything that followed. Inflation didn't just stretch space, it stabilized time. The rapid expansion diluted quantum chaos, allowing uniform physical laws to emerge. Without inflation, the universe might have remained turbulent and inconsistent, unable to form structure. When inflation ended, the energy that had driven it converted into matter and radiation, filling the universe with a hot, dense plasma. From there, the familiar sequence of cosmic events began: cooling, nucleosynthesis, recombination, and eventually the formation of stars and galaxies. But none of that could have happened without the Planck moment. It was the ignition point, the instant that turned possibility into process. Even though we can't observe it directly, we can still see its fingerprints. The uniformity of the cosmic microwave background, the evenness of temperature across the entire sky, tells us that everything we can see was once in causal contact. That means the universe was once small enough that all its parts could interact. The only way that could have happened is if inflation and the Planck scale expansion truly occurred. The universe remembers its beginnings in its structure. The smoothness of the cosmos is a memory of its first fractions of a second. The Planck moment also defines the limits of our understanding of time. If time began there, then asking what happened before is meaningless. There was no before in the way we understand it. Time didn't emerge from something else. It was the emergence itself. The Planck moment wasn't the start of an event. It was the start of the concept of events. From then on, everything had a place in the sequence. Every cause could have an effect. Every moment could follow another. Still, the idea that time has a beginning feels strange. We experience it as continuous, unbroken. The notion that there was once no before challenges every intuition we have. Yet from the perspective of physics, it makes sense. Time is part of the structure of the universe, not a separate backdrop. When the structure began, so did time. It's not that time appeared in a pre-existing space. Space and time came into being together, inseparable from the start. Some cosmological models suggest that the Planck moment may not have been an absolute beginning, but rather a transition, a bridge between two states. In cyclic models, the universe undergoes endless expansions and contractions, with each new expansion representing a new phase of time. In that case, the Planck moment could be the point where one universe ends and another begins. Time, instead of starting from nothing, might loop endlessly, with each cycle erasing the memory of the last. Other theories, like the ekpyrotic model, propose that our universe was born from the collision of higher dimensional brains, vast membranes existing in a space beyond our own. When they collided, the energy released created a new space-time, ours. In that view, the Planck moment wasn't the birth of everything. but the moment when our particular bubble of space-time separated from a larger, timeless reality. Whether the universe began once or begins endlessly, the Planck moment remains the line we cannot yet cross. Every scientific model runs up against it, and beyond it lies speculation. But even that limit has value. It tells us that reality has boundaries, not in space, but in knowledge. There are scales where our tools fail, where our understanding stops. Yet, even as a mystery, the Planck moment connects us to the most fundamental truth about existence, that from something so small, so brief, and so unreachable came everything that is. It's astonishing to consider how something so short-lived could give rise to time itself. In a sense, the Planck moment is still happening, its consequences never ended. The laws that emerge from it continue to govern every atom, every beam of light, every heartbeat. The expansion that began then has carried on for billions of years, stretching space-time further with every passing second. The moment that started it all hasn't vanished into history. It's embedded in the fabric of reality, present in every second that passes. When you think about the universe this way, time becomes less like a river flowing from a source and more like a field expanding outward, everywhere at once. The Planck moment wasn't a drop at the head of the stream, it was the spark that made the stream possible, and the flow that began there continues through everything, through galaxies, through the Earth, through you. Every motion you make, every breath you take, every thought that flickers in your mind is built on the laws that came into being in that first instant. The world around you, from the glow of a candle to the orbit of planets, is part of the same unfolding. When you look up at the stars, you're seeing the aftermath of the Planck moment stretched across cosmic time. The light from those stars is a record of the universe's earliest rhythms, the same ones that shape the flow of seconds you experience now. The birth of time wasn't a singular event that vanished into the past. It's a condition that continues to define the present. The Planck moment set the rules for how reality behaves, and those rules have been running ever since. You could say that we live inside the aftermath of that instant, or perhaps more accurately, inside its continuation. The Planck moment never truly ended. It only evolved. Its expansion became the unfolding of history. Its flicker became the rhythm of time. And as you lie here listening, feeling the slow, steady movement of your own breathing, you're connected to that origin. The time you experience, the quiet passing of seconds, is the same time that began in that unimaginable instant. The same field that once boiled with quantum foam now carries your heartbeat, your thoughts, your awareness. The universe's first moment is still unfolding, gently, through you. When the earliest universe began to cool and stretch, something remarkable happened. From that seething field of energy and particles emerged light, the first light, though not the kind we can see with our eyes. It wasn't the light of stars, because stars wouldn't exist for hundreds of millions of years. It was the light of the universe itself becoming transparent for the first time. Before this, the cosmos was shrouded thick with matter and radiation tangled together in an opaque haze. Then gradually the fog began to lift, and when it did, the universe's own radiance flooded outward, marking one of the most important transformations in all of cosmic history. To understand how this first light came to be, we need to go back to a time long before galaxies or atoms, when the universe was still a dense, hot plasma of particles and energy. In that early state, matter and radiation were trapped together. The universe was filled with photons, particles of light, but those photons couldn't travel freely. Every time they tried to move, they collided with charged particles like electrons and protons. The result was a universe that glowed but couldn't shine. Light existed, but it couldn't go anywhere. It was constantly absorbed and re-emitted, trapped in a blinding fog that no eye could ever see through. This period is known as the photon epoch, and it lasted for hundreds of thousands of years. During that time, the universe continued to expand and cool. As it did, the density of particles decreased and the collisions between light and matter became less frequent. Eventually, the temperature dropped low enough for electrons to combine with protons, forming neutral hydrogen atoms. That moment, when matter finally captured its free electrons, changed everything. For the first time, the universe became transparent to light. This event is called recombination, though it was actually the first combination of matter and electrons, not a reuniting. It happened roughly 380,000 years after the Big Bang. To us, that number sounds enormous, but compared to the billions of years that followed, it's a blink. When recombination occurred, the universe cooled to about 3,000 degrees Kelvin, roughly the temperature of the surface of a red star. At that temperature, atoms could remain stable without being torn apart by collisions. The fog lifted, and light, for the first time, could travel freely through space. The photons released in that moment have never stopped travelling. Over the billions of years since, they've been stretched by the expansion of space, their wavelengths lengthened from visible light to microwaves. Today we detect them as the cosmic microwave background, a faint glow that fills the entire sky, uniform in every direction. It's the oldest light in existence, the first visible trace of time's flow. When we look at it through our instruments, we're seeing the universe as it was at the moment it became transparent, a snapshot frozen in radiation. If you could somehow stand within that ancient light, it wouldn't look like a sunrise or a burst of brightness. It would be uniform all around you, glowing softly from every direction. It wasn't a flash or an explosion. It was a slow unveiling. The cosmos didn't light up suddenly. It eased into clarity, as though a mist was gradually lifting from an endless ocean. That transition marked the beginning of the universe we know, one where light could move, where energy could travel, and where structure could form. Before that, the universe was too chaotic for stable objects to exist. Photons collided so frequently that they prevented matter from gathering. Any attempt at forming structure would be immediately undone by the constant bombardment of light. Once photons were freed, that pressure dropped. Gravity could finally begin to draw matter together, laying the groundwork for the first stars and galaxies. In this way, light's release didn't just illuminate the universe, it made structure possible. It's strange to think that the light we detect today, those ancient photons that fill our instruments, has been travelling for nearly 14 billion years. Each one has crossed vast stretches of space, moving through the expansion of the cosmos itself. The distances between galaxies have grown so immense that the light has been stretched almost beyond recognition. Yet, it still carries information about the universe's earlier state. When scientists measure the tiny variations in that background radiation, they're reading the imprints of the universe's first imperfections, the faint ripples that would eventually become galaxies. Those ripples are the fingerprints of creation, preserved in light. The discovery of this radiation in the 20th century was one of the most important moments in science. It confirmed that the universe had a beginning, that it expanded from a hot, dense state, and that the glow of that beginning still surrounds us. Even though it's faint, only a few degrees above absolute zero, it's everywhere. No matter where you look, that first light reaches you. It's the oldest thing you can see, the universe's memory written in photons. To imagine the significance of that is to realize how deeply we live within the unfolding of that early event. Every source of light we know, the sun, the stars, the flicker of a candle, owes its existence to that first release. When light became free, matter could cool, coalesce, and ignite. The stars that would later shine across galaxies were made possible because the universe once learned how to let light go. The physics behind this freedom is elegant. Before recombination, free electrons scattered photons through a process called Thomson scattering. Every time a photon tried to travel, it encountered an electron and was deflected. Once electrons were captured by protons to form neutral atoms, there were far fewer free charges to scatter light. The photons, finally unbound, could stream through space uninterrupted. That transition from trapped to free light marks the last time the universe's matter and radiation were in perfect equilibrium. From that moment on, they went their separate ways, matter forming the scaffolding of galaxies, light spreading through the cosmos. When you think about light, it's easy to treat it as something ordinary. We live surrounded by it. We rely on it for warmth, sight, and energy. But light is the most fundamental messenger in the universe. It tells us everything we know about the cosmos. Every observation, every discovery, every glimpse into the past depends on light. The first light wasn't just illumination, it was information. It carried the first data, the first record of what the universe was like. Those photons are like ancient letters still arriving, telling us what the cosmos looked like when it first found clarity. If you could trace one of those photons backward, it would lead you to the edge of time, to the moment when light separated from matter and began its endless journey. It has been moving ever since, never slowing, never tiring, crossing the expanding universe without pause. That means the universe's first light is still around us, still streaming through every corner of space. When you warm your hands near a fire, you're feeling the same phenomenon, energy radiating outward as light. But that simple, familiar warmth is connected to something ancient and universal, the same process that first made the cosmos visible. There's a kind of symmetry in this. The first light marked the beginning of the universe's visible history, and every new light, every star that forms, every spark that burns, is part of that same ongoing illumination. The story of the universe is, in many ways, a story of light finding new ways to express itself. From the opaque plasma of the early cosmos to the first shining stars to the glow of galaxies, light has been the constant companion of time. Where light goes, time can be measured. Where time flows, light finds a way to move. After recombination, the universe entered a period often called the Dark Ages. Despite the name, it wasn't truly dark. The cosmic background still glowed faintly, but there were no stars, no new sources of light. The universe was filled with hydrogen and helium gas, cooling slowly, almost featureless. Gravity was quietly at work, pulling matter into denser regions, forming the first clouds that would one day collapse into stars. It would take hundreds of millions of years before those stars ignited and the cosmos filled with starlight. But the foundation was set during that first release of photons. The universe had learned how to transmit energy across distance, how to connect one region of space to another through radiation. In a sense, the first light was a bridge, a connection between what had been and what could be. Before it, the universe was a closed system, each part isolated by collisions and chaos. After it, the universe became communicative. Light carried information from one place to another. It became the medium through which the universe could know itself. The cosmic microwave background that we observe today is astonishingly uniform, but not perfectly so. Those tiny irregularities, fluctuations in temperature just a few millionths of a degree, are what allowed structure to form. Without them, the universe would have remained a smooth soup of matter and radiation forever. The slight variations, slightly warmer, slightly denser regions, gave gravity the seeds it needed to pull matter together. Over eons, those seeds became galaxies, stars, and planets. The light we see in the night sky today, the light that falls on oceans and forests, the light that reflects off your face in a mirror, all of it descends from that first glow. It's strange to realize that when you turn off the lights at night and think you're surrounded by darkness, you're still bathed in that ancient radiation. It's invisible to your eyes, but it's there, washing over you, passing through you. The universe never truly turned off its lights. It only changed their form. The microwave glow that fills the cosmos is a constant reminder that the beginning is still shining faintly all around us. every photon from that time is a survivor. It's travelled across an expanding universe for billions of years, stretched, cooled, and weakened, but never extinguished. It's the closest thing we have to a direct witness of creation. And it tells us something profound. The universe remembers. It remembers in light, in energy, in the way the faintest radiation still carries the signature of its birth. When you look up at the stars, you're seeing new light, born long after the first. But behind that light, in the depths of space, the first light still glows. It fills the background of every view, silent but ever present. You can't see it with your eyes, but it's there in every direction, in every moment, the quiet echo of the universe's awakening. And if you could somehow listen to it, you'd hear a kind of hum, not a sound in air, but a faint vibration in microwaves, a uniform whisper coming from everywhere at once. That hum is the afterglow of creation, the first light continuing to travel, indifferent to time, unstoppable in its persistence. It's the rhythm of the cosmos written in radiation, still playing softly in the background of existence. That light, stretched across space, connects you directly to the beginning. The photons that warm your skin on a sunny day are younger, but they are part of the same lineage, children of that first release. When light became free, the universe gained its voice. It learned how to send messages through time, and we, billions of years later, have learned how to listen. Every moment of light that touches you, every reflection, every sunrise, is a continuation of that event. The universe's first act of illumination never ended. It continues to unfold with every photon that moves through space, every second that passes, every awareness that turns toward the sky. And as that ancient light continues its journey, it carries with it not just the memory of the universe's beginning, but the quiet assurance that even in the vastness of time, something that once began still endures, still shines, still reaches across the dark. Once the universe had learned to carry light across its growing expanse, another force began to assert its quiet influence. It didn't glow, it didn't radiate, it didn't speak in brightness. It moved in silence, shaping everything that would ever exist without ever being seen. That force was gravity. From the very beginning, gravity has been the architect of the universe, subtle, patient, and relentless. While light made the universe visible, gravity gave it form. It turned the scattered energy of the early cosmos into structure, order, and motion. In the earliest times, the universe was astonishingly uniform. The matter and radiation left over from the Big Bang were spread almost perfectly evenly. The differences in density from place to place were minuscule, 1 part in 100,000. Yet those tiny variations were enough. Gravity doesn't need much to work with. Over billions of years, it can take the faintest imbalance and magnify it into entire galaxies. The story of gravity begins with space-time itself. According to Einstein's general relativity, gravity isn't a force in the traditional sense. It isn't something that pulls objects together through invisible strings. Instead, it's the curvature of space-time caused by the presence of mass and energy. Matter tells space-time how to curve, and curved space-time tells matter how to move. The result is what we experience as gravity, the reason apples fall, planets orbit, and light bends near stars. In the first moments after the universe began expanding, all 4 fundamental forces were unified. As it cooled, they separated. Gravity was the first to step apart, distinguishing itself from the others. That separation marked a turning point, the beginning of the universe's structure. Once gravity became distinct, it began shaping the flow of time and the behavior of matter. The same expansion that freed light also gave gravity the space to work. At first, its influence was weak compared to the intensity of radiation and energy in the young universe. The expansion was so rapid that gravity couldn't immediately gather matter together. But as the universe grew and cooled, radiation thinned and gravity began to take over. Slowly, imperceptibly, it started amplifying those small variations in density that had been imprinted in the early universe. Regions that were slightly denser than average began to attract more matter, growing denser still. Regions that were slightly less dense lost matter and became emptier. This process of amplification continued for millions of years, gradually turning the smooth early cosmos into a landscape of clumps and voids, the first scaffolding of cosmic structure. If you could have watched the universe then, you wouldn't have seen much. There were no stars yet, no galaxies, no planets. Everything was still dark. But if you could somehow feel gravity, you'd sense its quiet persistence, drawing matter together in invisible currents. It worked without rest, without pause, guided only by the geometry of space-time itself. It was as though the universe, having been born in expansion, now began to learn the art of gathering. The particles of matter that filled the early universe, mostly hydrogen and helium, moved under the influence of this growing structure. Wherever gravity had a slight advantage, those particles drifted toward one another, forming immense clouds. These clouds grew denser and cooler, collapsing under their own weight. In time, they would ignite as the first stars. But long before that happened, gravity was already shaping the universe into a pattern, a web of filaments and clusters stretching across space. That cosmic web still exists today. Every galaxy, every cluster of galaxies lies along those filaments of matter shaped by gravity's pull. The empty regions between them, the cosmic voids, are where gravity drew matter away. The scale is vast beyond comprehension, billions of light years across, yet the structure began with those faint whispers of density in the early universe. The same mathematical patterns that describe ripples on a pond can describe the formation of galaxies under gravity's influence. Simple rules, repeated endlessly, built everything. But gravity does more than shape space, it shapes time itself. The two are inseparable. In the presence of mass, time runs slower. Near a massive object, the curvature of space-time stretches the intervals between moments. This means that in a universe where matter is gathering, time itself is gathering too, flowing more slowly in some regions than in others. From the very start, gravity didn't just organize space, it organized the tempo of the universe. That difference in the flow of time might seem small on human scales, but across cosmic distances, it matters. In regions of high density, like those that would later form galaxies, time moved a little more slowly than in the emptier regions between them. Even now, this difference persists. A clock on the surface of the Earth runs slightly slower than one in orbit, and both run slower than one far from any massive body. Gravity doesn't just bind matter, it binds moments. This bending of time also affects light. When photons travel through regions of strong gravity, their paths curve and their energy changes. Like climbing out of a gravitational field loses energy, stretching to longer wavelengths, a process known as gravitational redshift. Conversely, light falling into a gravitational field gains energy, becoming bluer. These effects are subtle, but they reveal gravity's dual role as both sculptor of space and regulator of time. Every beam of light, every motion of a planet, every vibration of an atom is shaped by this quiet curvature. In the early universe, gravity's role was especially delicate. Too strong, and the universe would have collapsed back on itself before stars could form. Too weak, and matter would have scattered too quickly for galaxies to ever gather. Yet it balanced perfectly, just strong enough to slow the expansion slightly, just gentle enough to allow vast structures to emerge. This balance is one of the great mysteries of cosmology. Why should gravity have the exact strength it does? Why should it be tuned so precisely that life could eventually arise in one of its distant corners? Some physicists argue that there's no deeper reason. that the universe simply happens to have the properties we observe because in universes with other values, observers couldn't exist. Others suspect a hidden principle, a symmetry we haven't yet discovered, that dictates these constants. Either way, the result is the same. Gravity's whisper guided the cosmos into complexity, turning formless energy into a structured world. The earliest stars were born in the densest knots of gas drawn together by gravity. When those stars ignited, they produced light that illuminated the darkness for the first time since the cosmic background faded. Gravity had not only gathered matter, it had created the conditions for light to return in a new form. The first light of the stars was gravity's reward for patience, energy converted into brilliance after millions of years of silent preparation. Even now, gravity continues its work everywhere. It binds moons to planets, planets to stars, and stars to galaxies. It's the reason galaxies orbit one another in clusters, and why the universe's large-scale structure remains coherent even as it expands. It's also the reason stars die in spectacular explosions, collapsing under their own weight until new elements are forged. In every stage of cosmic evolution, gravity is both the destroyer and the creator, compressing and releasing, balancing and reshaping. On smaller scales, gravity governs the rhythm of everyday life. It holds you to the ground, shapes the air you breathe, and determines the path of every falling raindrop. When you drop an object and it falls, you're witnessing the same principle that moves galaxies. The curvature of space-time is guiding motion. The difference is only scale. The same geometry that bends starlight bends the trajectory of a pebble. What's most astonishing about gravity is how weak it is compared to the other forces. The magnetic attraction between two small magnets can easily overcome the gravitational pull of an entire planet. Yet, because gravity always attracts and never cancels out, it dominates on large scales. Over vast distances, it becomes the organizing principle of everything. It may be the weakest force, but it's also the most persistent. It never stops reaching, never fades completely. Scientists continue to search for its deeper nature. Unlike the other forces, gravity has never been fully integrated into the framework of quantum mechanics. We can describe it beautifully in the language of relativity, but at the smallest scales it resists quantization. The search for a quantum theory of gravity is a search for the missing piece of the puzzle, the rule that governed the universe during its first moments, when space-time itself was still forming. Perhaps one day we'll find it, and when we do, we may finally understand not just how gravity shapes time, but how it gave time its direction in the first place. In a way, every clock is a quiet homage to gravity. A pendulum swings, a planet orbits, a photon bends, all because space-time curves. When you mark the passage of seconds, you're counting the consequences of curvature. Time, as we experience it, is not separate from gravity. The two are threads of the same fabric. If you could somehow remove gravity from the universe, nothing would hold together. Galaxies would drift apart, stars would dissolve, planets would scatter. Even atoms might lose their structure, because gravity's geometry provides the underlying coherence of space-time itself. Without it, there would be no path for light to travel, no measure of time to compare. The universe would return to chaos, not through destruction, but through disconnection. Gravity is what makes connection possible. And yet, for all its power, gravity remains silent. It doesn't radiate, it doesn't shine, it doesn't make sound. It's present in every movement but never seen directly. Its presence is known only through its effects, through the way light bends, through the way things fall, through the slow swirl of galaxies. The first whisper of gravity in the early universe wasn't a sound at all but a shaping, a subtle rearranging of space-time that made everything else possible. That whisper continues. Every orbit, every rotation, every step you take is a response to it. The ground beneath you curves space-time ever so slightly, and you follow that curve with every movement. The same curvature that holds you here holds the moon in its path and the Earth around the sun. It's an ongoing dialogue between mass and geometry, a quiet conversation that began billions of years ago and never stopped. If you lie still and imagine the pull that keeps you anchored, you're feeling a faint echo of the force that once drew matter together from across the cosmos. That pull connects you to the galaxies, to the stars, to the very shape of time itself. Gravity's whisper was there at the beginning, guiding the flow of energy into form. It's still here now, patient and invisible, still writing the structure of the universe with the same quiet persistence it had in the first moments after creation. And somewhere, in the vast darkness between galaxies, gravity continues to hum its steady tune, the same one it began when time was young, a soundless rhythm that never fades, holding everything together as the universe continues its endless expansion, still balancing, still curving, still whispering. As gravity continued its slow, steady work shaping matter into structure, the universe itself never stopped stretching. Expansion wasn't a one-time event that happened in the past. It has been happening every moment since the first fraction of a second after the beginning. It continues even now, carrying galaxies farther apart, lengthening the distances between clusters, and stretching the very fabric of space. This expansion is not something occurring inside the universe. It is the universe. Every point in space is part of it, every second of time an expression of its ongoing motion. To imagine this expansion, it helps to think not in terms of explosions or motion through emptiness, but of growth from within. Imagine a balloon covered in dots. As the balloon inflates, the dots move away from one another, but not because they're travelling across the surface. The surface itself is expanding. The universe works in a similar way, though it has no edge, no centre and no outside. Every part of space stretches uniformly, so that from any point everything else seems to be receding. Wherever you are, you're at the centre of expansion, and so is every other point in the cosmos. This expansion is what cosmologists call the fabric of spacetime, stretching smoothly under the influence of energy and gravity. It's measured by what's known as the Hubble constant, which describes how fast galaxies move away from each other relative to their distance. When astronomers look at distant galaxies, they see their light shifted toward the red end of the spectrum, a phenomenon called redshift. That shift is the signature of expansion. As space stretches, the light travelling through it is stretched too, its wavelength elongated. The further away a galaxy is, the more its light has been stretched, meaning we see it as it was farther back in time. This is one of the most remarkable features of our universe. Looking out into space is the same as looking back in time. Because light travels at a finite speed, distant objects show us the past. A galaxy 1 billion light-years away appears as it was 1 billion years ago. The light from some of the most distant galaxies we can detect began its journey more than 13 billion years ago, not long after the universe became transparent. In this way, the expansion of the universe allows us to see its history written across the sky. As time passed, expansion and gravity worked together in a delicate balance. Gravity tried to pull matter together, forming galaxies and clusters. Expansion tried to pull everything apart. For billions of years, the two forces contended with one another, shaping the structure of the cosmos. The balance was never exact. Regions of space dense with matter slowed their expansion as gravity took hold, while emptier regions stretched more freely. The result was the vast cosmic web that now fills the universe. Filaments of galaxies and dark matter connected across unimaginable distances, separated by enormous voids of almost perfect emptiness. This vast structure is sometimes called the large-scale tapestry of the universe, and it's not a metaphor. When astronomers map the positions of galaxies in 3 dimensions, what emerges looks uncannily like a woven network. Threads of light and matter stretching across the dark, meeting at dense intersections where galaxy clusters reside. Between them are enormous expanses where almost nothing exists. These voids are hundreds of millions of light-years wide, but they aren't truly empty. They contain thin wisps of gas, dark matter and radiation, remnants of the early universe still drifting through the expanding fabric of space. The tapestry isn't static. Every thread, every cluster, every filament is still moving. The universe continues to expand, and the distances between the threads increase. Galaxies within clusters remain bound by gravity, but clusters themselves drift farther apart. Over cosmic timescales, the web is stretching, growing thinner and more diffuse, though its overall pattern remains the same. It's a living structure, dynamic and evolving, with time as its invisible loom. The cause of this expansion lies in the energy of space itself. In Einstein's equations, space is not empty. Even in the absence of matter or radiation, space has energy, what physicists call the cosmological constant, or more broadly, dark energy. It acts like a pressure that pushes space to expand. When the universe was young and dense, gravity dominated, slowing the expansion. But as space grew and matter spread out, dark energy became more significant. Over the past few billion years, it has taken over as the main driver of cosmic evolution. The expansion of the universe is no longer slowing down, it's accelerating. This acceleration is one of the great mysteries of modern cosmology. We can measure its effects precisely, but we don't yet know what causes it. Dark energy seems to make up nearly 70% of the total energy content of the universe, yet it's invisible, undetectable except through its influence on expansion. It doesn't clump like matter or radiate like light. It's uniform, filling every region of space equally, and as the universe grows, more of it appears. The fabric of space-time isn't stretching into something, it's generating itself. Every moment of expansion brings more space, and with it, more energy. This idea that the universe creates more of itself as it grows is hard to grasp. We're used to things expanding into something else, like air filling a room or a wave spreading across water. But the universe doesn't expand into emptiness. The expansion is the creation of new space-time. Every second, the distances between galaxies increase, and the universe contains more of everything that defines it. More space, more time, more of the field that underlies existence. The total energy may still balance to zero, with positive energy from matter and radiation offset by the negative energy of gravity, but the amount of structure keeps increasing. The implications are vast. If the acceleration continues indefinitely, galaxies beyond our local cluster will drift so far away that their light will never reach us again. Over immense spans of time, the observable universe will shrink, not because space is collapsing, but because expansion is carrying distant galaxies beyond the reach of light. Eventually, only the galaxies bound together by gravity, our local group, will remain visible. The rest of the cosmos will fade into darkness, its light stretched beyond detectability. Future observers, living trillions of years from now, may see only their own galaxy, unaware that the universe ever extended beyond it. Yet, in our time, the universe is still young enough that we can see the tapestry in full. The light from billions of galaxies reaches us, each one a point in a vast pattern that spans the visible sky. When astronomers study this pattern, they find remarkable consistency. The distribution of galaxies follows the same statistical rules across scales, from small clusters to immense superstructures. This self-similarity hints at the simplicity of the early universe, that everything began from uniform conditions, shaped only by the laws of physics and the influence of gravity. The expansion of the universe also affects the flow of time. In regions where space expands faster, time moves differently. The relationship between expansion and time is subtle but real. The more space stretches, the longer it takes for light to travel between points, which means the experience of time itself depends on the rate of expansion. On a cosmic scale, time and expansion are inseparable. Every increase in distance between galaxies is accompanied by an increase in the universe's age. To say the universe is expanding is the same as saying time is continuing. Even within this immense process, the physics that governs it is simple in its elegance. The universe expands because it must, because the equations of relativity describe a dynamic spacetime, one that cannot remain static unless finely tuned. Einstein himself initially resisted this idea. He introduced the cosmological constant to balance his equations, hoping to describe a static universe. Later, when observations showed that galaxies were receding, he reportedly called the constant his greatest mistake. Ironically, it now appears that the cosmological constant, or something like it, is real after all. Not to keep the universe static, but to explain why it expands ever faster. It's easy to think of expansion as a kind of outward motion, but that isn't quite right. On small scales, within galaxies, solar systems, or atoms, gravity and other forces hold matter together tightly enough to resist expansion. The space between planets doesn't grow, neither does the space between you and the chair you're sitting on. Expansion operates on the larger scales, where matter is sparse and gravity too weak to hold it all together. The fabric of space stretches between galaxies, but not within them. This is why the night sky still looks stable, even though the universe is swelling beneath it. Over billions of years, the balance between expansion and gravity has created the cosmic architecture we observe. Galaxies form in clusters. Clusters link into filaments. Filaments weave into superclusters. The pattern resembles a web not just in shape, but in function, a network through which matter and energy flow. This web evolves slowly, almost imperceptibly, but it's always moving. Expansion pulls it wider, gravity pulls it tighter. Together they maintain the dynamic equilibrium of the cosmos. When you look at an image of deep space filled with galaxies stretching to the limits of visibility, you're seeing this tapestry in cross-section. Every point of light is a galaxy containing billions of stars, and every one of those galaxies lies along one of the threads that began forming billions of years ago. The darkness between them is not empty but expanding, stretching the distances between clusters faster than light can cross them. Even as we observe them, those galaxies are moving away, carried by the very expansion that makes their light reach us redder and older. This expansion is not uniform forever. On very long timescales, its behavior could change. If dark energy remains constant, the acceleration will continue, driving galaxies apart until only isolated islands of matter remain. If dark energy itself evolves, as some theories suggest, the expansion could slow or even reverse. In that case, the universe might one day contract, collapsing back toward a dense state, perhaps leading to another cycle of rebirth. The ultimate fate of the tapestry is still uncertain, but for now it continues to stretch, weaving new patterns from the threads of time and matter. And while this cosmic motion unfolds on scales too vast for us to feel directly, we are part of it. The atoms in your body are carried along by the same expansion that moves galaxies. The space between molecules doesn't grow, but the space that contains everything, from the Earth to the most distant quasar, does. You're riding the expansion of the universe every moment of your life without noticing it. Time, as you experience it, is the local expression of that same cosmic unfolding. There's a quiet wonder in realizing that the vastness above you and the moments within you are governed by the same principle. The universe expands, and so does the space of your awareness. Every second that passes is another pulse in the same cosmic rhythm that began billions of years ago. You're not separate from the expansion, you're made of it. The time flowing through your thoughts is the same time that carries galaxies away from one another, the same fabric stretching beneath stars and between atoms. The universe's expansion isn't just a feature of reality, it is reality. Every structure, every process, every life exists within it. It defines the possible and the observable. Without it, there would be no time, no change, no history. Expansion is the heartbeat of existence itself, steady and unstoppable, carrying everything that is forward through the quiet depths of space. And as that tapestry continues to stretch, it carries with it the faint light of the first stars, the soft whisper of gravity, the memory of the universe's own beginning. Somewhere, at the farthest reaches of visibility, photons are still travelling from the first galaxies, still moving across the widening fabric, still reminding us that the expansion hasn't ended, that it never has. The same motion that began with the birth of time still unfolds now, silent and continuous, carrying us all further into the endless expanse that is both our home and our history. As the vast fabric of the universe stretched and cooled, the flow of time became more than a cosmic backdrop. It began to manifest within things, inside the movements of matter, inside the cycles of energy, inside the patterns that would later become stars, planets, and life. The expansion of space gave time its universal direction, but within that expansion, smaller rhythms began to appear. These were the first clocks, not in the mechanical sense we know, but in the physical sequences that mark duration, oscillations, rotations, orbits, vibrations. Out of chaos, time began to find its local expressions. In the earlier stages, time had no regularity. The universe was still a turbulent ocean of energy, with matter and radiation colliding, scattering and forming new combinations. But as expansion continued, the temperature dropped, and energy began to condense into stable forms. Elementary particles gained mass, forces separated into their familiar roles. The randomness began to settle into structure. It was in that settling that the first measurable intervals appeared, processes that could repeat, creating rhythm out of disorder. Every physical process, from the vibration of an atom to the rotation of a planet, can serve as a clock. A clock, at its most fundamental level, is simply anything that repeats predictably. When the first atoms formed, they brought with them a natural rhythm, electrons orbiting nuclei, emitting and absorbing energy in specific quantized steps. Those transitions define the most precise clocks we know today. But their origin lies in the same physics that emerged when the universe cooled enough for stable atoms to exist. In that sense, time didn't just begin at the Big Bang, it crystallized gradually, finding ways to express itself through the organization of matter. As the universe became more structured, it developed systems that could keep time, not consciously, but physically. The cosmic microwave background is one example. The ripples within it oscillate, creating patterns that correspond to the density fluctuations in the early universe. These oscillations, known as acoustic peaks, are like the heartbeat of the cosmos during its infancy. Periodic compressions and rarefactions in the primordial plasma. Long before stars or planets, the universe already had its first rhythm. Those ripples in the plasma left their imprint on the structure of the universe we see today. The distances between galaxies and clusters still carry the signature of those early oscillations, a relic of the first universal ticks of time. On that scale, the cosmos itself functioned as a clock, one so vast that its pulse continues to shape the distribution of matter billions of years later. But as the universe grew, smaller and more intricate clocks began to emerge. Gravity gathered matter into stars, and stars introduced new cycles. The burning of fuel, the oscillation of brightness, the birth and death of light. A star's life is a long, complex clock defined by nuclear fusion. The rate at which it shines is set by the balance between gravity's inward pull and the outward pressure of energy. That balance determines how long it lives, how it evolves, and when it will fade. The ticking of that stellar clock can last millions or billions of years, but it's as regular, in its own way, as the swing of a pendulum. Inside those stars, smaller clocks ticked faster. Nuclear reactions happening at astonishing speeds, creating heavier elements atom by atom. Each reaction followed precise rules, governed by temperature, density, and quantum mechanics. The universe's first atomic forges were also its first chronometers of transformation, measuring time not in seconds, but in the conversion of matter to light. As stars aged and died, their explosions scattered those heavier elements into space, seeding the cosmos with the materials that would one day form planets and living beings. The cycles of starbirth and death introduced a new kind of rhythm, one not just physical but generational. The universe began to inherit its own history, building each new structure from the remnants of what came before. In that way, time acquired memory. On smaller scales, time found expression in rotation. The swirling clouds of gas and dust that surrounded newborn stars began to spin, flattening into disks under the influence of gravity and angular momentum. Within those disks, tiny grains of matter collided and stuck together, forming planets. Each of these rotating systems became its own clock, a steady, repeating motion that measured the passage of days, months, and years. The universe was creating natural metronomes at every scale. When the Earth eventually formed, its own rotation became the basis for time as humans would later understand it. The turning of the planet gave rise to the cycle of day and night, while its orbit around the sun created the seasons. Long before any creature could name them, these cycles provided the most ancient and reliable clocks, the ones that defined the rhythm of life itself. But even before life arose, time had begun to accumulate complexity. The interplay between chaos and order produced not just repetition but variation, irregularities that would one day make evolution possible. The universe's clocks were not perfectly synchronized. The rotation of planets, the pulsation of stars, the vibrations of atoms all ticked at different rates, creating a rich and varied texture of time. This diversity is what made the cosmos dynamic. If everything ticked in perfect unison, nothing would ever change. It's the small differences in timing that allow complexity to emerge. In the language of physics, this interplay is captured by entropy, the measure of disorder in a system. Entropy gives time its direction. It ensures that processes move from order to disorder, from high energy to low. Every clock, every repeating cycle, operates against this background of increasing entropy. It's what allows time to feel like it's moving forward, even though the fundamental laws of physics themselves don't prefer one direction over another. The arrow of time. The reason yesterday is different from tomorrow comes from the statistical behavior of countless microscopic interactions. That arrow first took shape in the early universe, when energy and matter began to separate and the uniformity of the cosmos gave way to structure. From that moment onward, entropy has been increasing. The universe's expansion provides the stage for this increase. As space grows, energy spreads out, allowing systems within it to evolve toward greater complexity. Stars burn their fuel, galaxies drift apart, and even within atoms, particles lose energy through radiation. Each of these processes marks the advance of time through entropy's rise. On Earth, that same principle governs the passage of moments you can feel. A melting ice cube, a fading echo, a burning candle, all are tiny expressions of the same universal trend toward greater disorder. Yet, within that disorder, new forms of order can emerge. Life, for example, depends on taking in energy and releasing it as heat, maintaining internal order while contributing to the universe's overall entropy. Even consciousness, the awareness of time passing, arises from patterns of change in the brain that rely on this constant flow of energy. When you think about time as a physical quantity, you begin to see how deeply it's embedded in everything. A pendulum swings because of gravity's curvature. A quartz crystal oscillates because of atomic vibrations. The flow of electricity through a circuit, the decay of radioactive isotopes, the revolution of a planet, all can serve as measures of time because all are processes governed by the same laws that arose after the universe's first cooling. There's no single master clock ticking above it all. Instead, there are countless interconnected clocks, each marking its own rhythm, each synchronized loosely through the geometry of spacetime. Even the universe itself functions as a kind of clock. Cosmologists describe its age not just as a number, but as a consequence of its expansion rate. As space grows, the time since the Big Bang increases, defining a universal timescale for cosmic history. Yet, within that grand timescale, every galaxy, every planet, every atom measures its own passage differently. Time is both global and local, continuous and relative. It flows differently depending on gravity, motion and energy. There's no single tick that applies everywhere. Time is woven from differences. At human scales, we've built our own versions of these cosmic clocks. We measure time with increasing precision, from the movement of celestial bodies to the oscillations of atoms. The second, as we define it, is based on the frequency of light emitted by cesium atoms, a rhythm so precise it drifts by less than a billionth of a second in a year. In that way, we've learned to mimic the universe's own processes, creating instruments that echo the stability of fundamental physics. Our clocks are miniature reflections of the cosmic order, fragments of the larger timing that began when the universe first expanded. And yet, no matter how precise our measurements become, time itself remains elusive. We can quantify its passage, but we can't stop it, reverse it, or isolate it. It's not a thing that flows, but a relationship between events. When one process changes relative to another, we call that change time. The universe doesn't have an external clock counting down its existence. It is the counting, every transformation, every decay, every expansion a mark on its own unfolding. In the midst of all this motion, chaos never disappeared. It's still there, woven into the fabric of the cosmos. But within that chaos, patterns continue to emerge, cycles that bring order, systems that maintain balance, beings that perceive rhythm. The clocks within the chaos are what allow meaning to form. They let structure arise in a universe that would otherwise drift endlessly toward uniformity. Time's local expressions are the stabilizing anchors of a changing cosmos. When you look at a night sky, you're seeing countless clocks running at once. Each star is aging at its own pace, each galaxy rotating, each photon moving toward you along a path defined by curvature and expansion. The light you see from a star may have left it millions of years ago. That light's journey is a measurement, a line drawn across space-time carrying information from one moment to another. In a sense, every beam of starlight is a clock, measuring the distance between then and now. The same is true within you. The rhythm of your heart, the oscillations of your neurons, the cycles of sleep and waking, all are time made tangible. You're a system of clocks within clocks, from the spin of particles to the beating of your pulse. Each of those rhythms traces its origin back to the same unfolding that began when the first patterns of time appeared in the young universe. You're a continuation of those rhythms shaped by their persistence. The chaos of the cosmos never truly ended. It only became structured. And within that structure, every repeating process, every stable orbit, every heartbeat carries forward the legacy of time's earliest organization. The universe's clocks are still ticking, from the slow drift of galaxies to the rapid vibration of atoms. As the universe grew older, the chaos that once defined it began to settle into patterns. Expansion slowed just enough for gravity to gather matter into familiar shapes, and within those shapes, motion found consistency. For the first time, the universe began to keep steady time. It wasn't marked by clocks or calendars, but by the harmony of motion itself. Time, which had once been an abstract dimension of change, began to manifest as rhythm. In the beginning, every process had been random. Energy flickered unpredictably, collisions occurred at uneven intervals, and no repetition endured long enough to matter. But as the temperature fell and the density decreased, order began to emerge. The first stars formed, ignited, and shone steadily. The first galaxies took shape, rotating slowly under the pull of gravity. In those rotations, in those steady cycles of fusion and radiation, time began to find its rhythm. The rotation of galaxies is one of the universe's most enduring patterns. Each galaxy, with hundreds of billions of stars, spins as a single coherent structure. The stars within it orbit the center, completing revolutions that can take hundreds of millions of years. Yet, for all their scale, those rotations are astonishingly stable. A spiral galaxy, viewed from above, appears almost motionless, but in reality it's a vast clockwork. Every star a gear, every orbit a beat in the long rhythm of cosmic time. This regularity didn't appear by chance. It's the outcome of gravity-balancing motion. When gas clouds collapse under their own weight, they begin to spin faster, conserving angular momentum. That spin stabilizes the structure, preventing it from collapsing completely. Over time, these rotating systems settle into equilibrium. The balance between rotation and gravity gives galaxies their shape, just as it gives planets their orbits. It's a simple principle repeated endlessly, from the smallest systems to the largest. The same process governs stars and planets. Around a young star, the material in its disk begins to clump together. The clumps grow, their gravity increasing until they form planets. Each planet inherits the motion of the disk, a rotation and an orbit. These motions become reliable markers of time, cycles that repeat without fail. The length of a day, the span of a year, the tilt of a season, all emerge from the steady rhythm of celestial motion. Before long, the universe was full of these natural timekeepers. Stars pulsed with regular brightness, planets rotated and orbited, moons moved in predictable patterns. Light travelled across space at a fixed speed, giving each distance a measurable delay. From chaos came predictability, and from predictability came rhythm. The universe, once a storm of unpredictable change, had become a symphony of repeating motion. Even within stars, rhythm took hold. Many stars oscillate in size and brightness, their outer layers expanding and contracting in cycles that can last hours, days, or years. These pulsations are not random. They're driven by the balance between gravity's pull inward and pressure's push outward, the same forces that define a heartbeat. In fact, some variable stars are so consistent that astronomers use them to measure distance across the cosmos. Their pulses are steady enough to serve as cosmic clocks. In this way, the universe developed layers of rhythm. On the grand scale, galaxies rotate. On the intermediate scale, stars pulse. On the small scale, atoms vibrate. Every layer contributes to the great temporal texture of the cosmos. Time no longer existed only as an abstract flow. It became tangible, expressed in cycles and oscillations, in repeating motion and balance. These natural rhythms gave rise to stability, and stability made structure possible. Once cycles became reliable, matter could settle into predictable configurations. Stars could form planetary systems that endured for billions of years. Planets could maintain climate stable enough for complex chemistry to arise. The steady rhythm of time made persistence possible, but rhythm didn't mean stillness. The universe remained in motion, always changing, always evolving. What made it rhythmic was the balance between repetition and variation. The way patterns could endure even as their details shifted. A galaxy might spin steadily, but within it stars are born and die, light brightens and fades, planets form and dissolve. The rhythm of the cosmos is one of continuity within transformation. Each beat contains change, but the overall tempo remains. In physics, this kind of rhythm is described by periodicity, the repetition of a process at regular intervals. Periodicity appears everywhere, in the vibrations of atoms, in the rotation of planets, in the waves of light. It's one of the most fundamental features of the universe. Without it, we couldn't define frequency, energy, or even temperature. Every stable system, from the smallest particle to the largest galaxy, is a form of rhythm. Light itself is rhythmic. Every beam of light is an electromagnetic wave, oscillating at a specific frequency. The colour of the light depends on how fast it oscillates. Blue light vibrates more rapidly, red light more slowly. When you look at the glow of a star, what you're seeing is the sum of countless oscillations, billions of vibrations per second, perfectly regular, perfectly rhythmic. The universe's radiance is made of rhythm. Even the concept of temperature, how hot or cold something is, depends on rhythm. Temperature measures the average energy of motion within matter. When atoms vibrate more quickly, the temperature rises. When they vibrate more slowly, it falls. In that sense, temperature is a measure of the rhythm of particles. Everything that has warmth, from a star to your own skin, is vibrating with the rhythm of time at the microscopic level. Over billions of years, these rhythms have guided the evolution of structure, from galaxies to life. They've set the pace for everything that exists. The Earth's orbit defines the rhythm of seasons. Its rotation defines the rhythm of day and night. The Moon's orbit creates tides that pulse across the oceans. Those tides, rising and falling over millennia, helped shape the conditions for life's emergence. Even biological processes, from the beating of a heart to the growth of a cell, evolved in harmony with these cosmic cycles. On our planet, time found a new kind of rhythm: biological time. Every organism keeps its own clock, a network of chemical and electrical oscillations that synchronize with the world around it. The circadian rhythm, roughly 24 hours long, governs the behavior of nearly all life on Earth. It's driven by molecular feedback loops inside cells that rise and fall in a steady pattern. Those internal clocks evolved in response to the planet's rotation, aligning life's processes with the alternation of light and dark. This synchronization between the cosmic and the biological is profound. The rotation of the Earth, the orbit of the Moon, the light from the Sun, all ancient rhythms set by the physics of motion, became the heartbeat of life itself. Each breath you take, each cycle of waking and sleeping, is tied to patterns billions of years old. Time's rhythm extends from the motion of galaxies down to the pulse in your veins. Even on much smaller scales, the same principle holds. Inside every atom, electrons move between energy levels in quantized steps, absorbing or emitting light of specific frequencies. These transitions define some of the most precise rhythms in the universe, the same ones used in atomic clocks to measure seconds with extraordinary accuracy. Time's rhythm is embedded in the fundamental laws of quantum mechanics, woven into the way energy and matter interact. The emergence of these consistent patterns marked a turning point in the story of the universe. Before, time was a measure of change without repetition, a sequence of unpredictable transformations. After, time gained regularity. The universe could now evolve in ways that built upon themselves, each moment connected predictably to the next. That predictability allowed complexity to grow, but time's rhythm isn't perfect. It varies across space and circumstance. In regions of intense gravity, time slows. Near the edge of a black hole, it almost stops. In regions where space expands more quickly, time seems to flow faster. This unevenness is part of the texture of space-time. The rhythm of the universe is not uniform. It's a composition of countless tempos, overlapping and interacting. Together they create a cosmic harmony, not mechanical, but dynamic, alive with variation. Even on Earth, time's rhythm shifts subtly. The planet's rotation slows over long periods due to the pull of the Moon. Days lengthen by fractions of a second every century. Atomic clocks must be adjusted occasionally to stay aligned with this gradual change. These tiny adjustments remind us that even the most stable rhythms are part of a living system, evolving slowly with the universe itself. And though time's rhythm feels steady to us, we're constantly moving through layers of it. The second-by-second rhythm of your heartbeat overlays the slower rhythm of your circadian cycle, which in turn follows the still slower rhythm of the Earth's orbit. Above that, the solar system moves through the galaxy, and the galaxy moves through the expanding cosmos. Each of these motions adds another layer of rhythm, another measure in the universal symphony. What's remarkable is that all these rhythms, from atomic vibrations to galactic rotations, coexist seamlessly. They don't interfere, they align through the consistency of physical law. The same constants govern every level of reality, the same speed of light, the same gravitational curvature, the same quantum rules. This consistency is what makes rhythm possible. It's why time flows smoothly instead of fracturing into chaos. The universe is vast beyond comprehension, yet it keeps perfect coherence. In this coherence, we find meaning. Rhythm allows prediction, and prediction allows memory. Without rhythm, there could be no continuity, no awareness, no history. The steady recurrence of patterns is what makes cause and effect possible. It's what allows us to experience the world as an unfolding sequence instead of an unconnected storm of events. Time's rhythm is the thread that binds reality together, and it's still changing. The rhythms that govern the universe are not eternal. They evolve. Stars burn out. Orbits shift. Even the expansion of the universe alters its own pace. The cosmic metronome ticks onward, but its beat slowly stretches, like a song played in ever larger spaces. One day, the stars will fade, and the galaxies will drift beyond each other's sight. The great rhythm will slow into near silence, but it will not stop. Time doesn't end when its patterns fade. It continues, patient and unhurried, waiting for whatever comes next. The rhythm you live by, the movement of days and nights, the cycles of breath and thought, is part of this same continuum. The laws that shaped the first galaxies also shape the neurons in your brain, the beating of your heart, the ticking of your inner clocks. You're not separate from time's rhythm. You're one of its expressions. Every pulse within you echoes the expansion of the universe, every thought another note in the long harmony that began when time first found its balance. And as you listen now, breathing softly, aware of each passing moment, you're feeling that rhythm from the inside. The same cosmic pulse that began when the universe discovered repetition, when motion became predictable, and when time learned how to keep its own beat. It hasn't stopped since. It moves through everything, through stars, through matter, through life itself. The rhythm that began billions of years ago continues still, quietly within you. As the universe settled into its long rhythm, as galaxies turned and stars pulsed and matter followed its steady cycles, something unexpected began to emerge from human curiosity. We looked at the regularity of time, at the apparent flow of moments, and began to wonder whether that flow was real or just how we perceive the unfolding of change. It's a strange thought. That time, the very thing that defines everything we do, might not exist in the way we imagine it. Yet, this idea has grown stronger the deeper science has looked into the laws that govern the universe. For most of human history, time felt obvious. It was the cycle of the sun and moon, the changing of seasons, the rhythm of life and death. It flowed in one direction, steady and irreversible. Even when people began to measure it with clocks, it remained a simple idea, an invisible line carrying everything from the past toward the future. But as physics advanced, that simplicity began to dissolve. The deeper we probed into the fabric of reality, the less certain time seemed to be. Einstein's theory of relativity was the first major step in reshaping our understanding. It revealed that time is not universal. It doesn't flow at the same rate everywhere. It bends, stretches, and slows depending on motion and gravity. Two people moving differently through space will experience different durations between the same events. Their clocks will tick at different speeds, not because of mechanical error, but because time itself behaves differently for them. That realization was revolutionary. It showed that time is not an independent stage on which the universe unfolds. It's part of the universe's structure. Space and time are woven together, forming the flexible geometry of space-time. What we experience as the flow of time is simply the way we move through that geometry. There is no single, universal now. Every observer carries their own slice of reality, their own sequence of events. This relativity of time leads to one of the most profound consequences in all of physics, the idea of the block universe. In this view, all of time, past, present and future, exists simultaneously. The universe is not something happening, but something that is. Each event, from the birth of the stars to this very moment, occupies a position in space-time, fixed and eternal. The flow we feel is an illusion of perspective, the result of consciousness moving along one path through the four-dimensional block. If this idea is right, then change doesn't really happen. The entire history of the universe is already laid out, every cause and every consequence existing together in a single timeless whole. We perceive time because we can't see the whole structure at once. We move through it, one slice at a time, and that movement gives rise to the sensation of past and future. It's a difficult concept to accept. We experience time so vividly, the feeling of moments passing, the awareness of memory and anticipation, that the idea of timelessness seems almost absurd. Yet the mathematics of relativity points firmly in that direction. In its equations, time doesn't flow. It's a coordinate like height or width, describing the position of events within the structure of space-time. Some physicists and philosophers find this deeply unsatisfying. If time doesn't flow, how can there be change? How can entropy increase? How can we grow older? To reconcile this, some propose that time is not fundamental but emergent, a property that arises only when certain conditions are met, much like temperature or pressure. Temperature, for instance, doesn't exist at the level of individual particles. It emerges from the collective behaviour of trillions of them. Perhaps time works the same way. In this view, the universe at its most basic level is timeless. The equations that describe its deeper structure, such as those in quantum mechanics, don't contain a time variable. They describe relationships between states, but not an external ticking clock. Time, then, would be a kind of approximation, something that appears when matter and energy interact in complex ways. It would be an emergent illusion created by change itself. One of the key clues supporting this idea comes from quantum gravity, the still developing attempt to unite general relativity with quantum mechanics. Some approaches, like the Wheeler-DeWitt equation, describe the entire universe as a static quantum state. In that formulation, time doesn't appear at all. The universe simply is a single, unchanging whole described by probabilities. Time only appears when parts of that whole are compared to one another. It's not an independent feature, but a relationship between states. That means what we call the flow of time might arise from correlations, from the way one system evolves relative to another. When we measure time passing, what we're really noticing is change, a pendulum swinging, a planet rotating, a neuron firing. Time isn't a background against which change happens, it's the measure of change itself. Without change, the concept of time would have no meaning. Some physicists, such as Carlo Rovelli, have argued that this relational view of time is the most natural one. In his formulation, called relational quantum mechanics, there is no single, absolute time. Each system in the universe keeps its own time through its interactions with others. The universe doesn't have one clock. It has countless local clocks, each defining the rhythm of reality for the things it touches. From this perspective, time is a web of relationships rather than a single, flowing entity. This way of thinking also helps explain why time seems to move forward, even though the fundamental laws of physics don't prefer any direction. At the microscopic level, those laws are reversible. If you filmed the motion of atoms and played it backward, the equations would still hold true. But on larger scales, we experience an arrow of time, a clear distinction between past and future. That arrow arises from entropy, from the statistical tendency of systems to move from ordered states to disordered ones. In a timeless universe, entropy becomes the key to how we perceive time. As entropy increases, information is lost, and the universe gains a sense of direction. Memory exists because physical systems can store information about their earlier states. You remember the past because your brain structure has been shaped by it. The future can't yet be remembered because it hasn't left an imprint. The arrow of time, in this sense, is not a fundamental law but a reflection of how information spreads and decays. Another way to think about timelessness comes from quantum cosmology. Some interpretations suggest that before the Big Bang, the universe existed in a timeless quantum state, a superposition of all possible configurations. Time began only when the universe expanded and matter formed relationships. That transition from quantum timelessness to classical time might explain why the laws of physics at the smaller scales look so different from those at larger ones. The Big Bang, in this view, wasn't just the beginning of space, it was the beginning of time as a perceivable property. If that's true, then time might not exist outside the universe at all. Asking what happened before the Big Bang would be meaningless because there was no before. The question assumes a timeline that didn't yet exist. Time is internal to the universe, not external. It's like asking what's north of the North Pole. The question dissolves when you understand the geometry. Some researchers go even further, proposing that time is a byproduct of entanglement, the quantum phenomenon where particles remain connected across distance. When two systems interact, they become entangled, and their states evolve relative to each other. That evolution creates a kind of internal clock. In this view, time emerges not from the universe as a whole, but from the relationships between its parts. Wherever there is interaction, there is time. Wherever there is isolation, there is timelessness. This relational understanding of time has surprising implications. It suggests that in regions of extreme isolation, such as deep space or within black holes, time might behave differently, or even cease to have meaning altogether. Inside a black hole, for instance, gravity warps spacetime so intensely that time for an outside observer seems to stop at the event horizon. But from the perspective of something falling in, time continues normally. The boundary between time and no time is not absolute. It depends on perspective. All of this leads to a curious realization. Our experience of time may be unique to beings like us, creatures that exist in a world of change, entropy, and memory. In a perfectly static universe, there would be no distinction between moments, and thus no awareness of passage. Consciousness itself may depend on time's asymmetry, on the ability to remember one state and anticipate another. Without that asymmetry, thought might not be possible at all. If time is emergent, then so is our perception of it. The feeling of flow, the sense that moments come and go, may be a mental construction built on physical processes that operate outside our awareness. Our brains, like all systems, rely on change to function. Neurons fire, chemicals diffuse, patterns form and dissolve. In the aggregate, those processes create the illusion of continuity. But underneath, the universe may be a frozen landscape of states, a timeless pattern in which everything that can happen already has. This possibility doesn't make time less meaningful. If anything, it makes it more extraordinary. To think that our sense of the present arises from the structure of reality itself, from the interplay between entropy, information, and perception, gives time a kind of quiet majesty. Even if it isn't fundamental, it is real to us, woven into the fabric of how we exist. Some scientists have tried to imagine what it would mean to truly step outside of time. Not just metaphorically, but physically. What would the universe look like from a timeless vantage point? Perhaps it would appear as a vast geometric structure, every event and every particle frozen in its proper place. A single, infinite pattern containing everything. Not static in the way of stillness, but complete. In that picture, nothing ever happens because everything simply is. Motion, change, life. All would be aspects of the structure itself, not processes unfolding within it. It's difficult to picture because our minds evolved within time, We experience reality through sequences, not wholes. We remember, we predict, we move, all of which depend on time's direction. To think of a world without it is to think beyond the limits of experience. And yet physics invites us to try, because the equations demand it. Whether time is fundamental or emergent remains an open question. Both views may be true, depending on scale. On human scales, time feels solid, measurable, inescapable. On quantum scales, it dissolves into relationships and probabilities. Perhaps time, like light, behaves differently depending on how you look at it. It can be both continuous and discrete, both flow and structure. Whatever its nature, the experience of time gives meaning to existence. It allows stories to unfold, causes to lead to effects, and life to have a sequence. Even if, in some deeper sense, time doesn't truly flow, our perception of its rhythm is real as the universe that created it. We live within that rhythm, shaped by it, bound to it, and perhaps defined by it. And as you sit quietly, listening, the seconds continue to pass. Not because time is moving, but because you are. The universe, in all its complexity, keeps changing, and with that change, time appears. Whether it's fundamental or emergent, absolute or relational, its presence is the thread that connects everything, from the smallest vibration of an atom to the widest stretch of space. If there is timelessness at the core of reality, it doesn't erase time, it contains it. The flow we feel might be just one perspective on a deeper stillness, a stillness that includes every heartbeat, every orbit, every moment that ever was or ever will be all at once, all together in the quiet geometry of the universe itself. When we speak about the beginning of time, it's easy to picture it as a starting point, a line emerging from darkness, a single instant before which there was nothing. But in physics, that idea becomes slippery. If time itself began at the Big Bang, then before has no meaning in the way we normally understand it. There was no ticking clock waiting to start, no empty void anticipating creation. Yet, the question still presses forward. What, if anything, existed before the beginning? It's one of the oldest questions in science and philosophy, and it has a quiet persistence that refuses to fade. Even knowing that time began with the universe, we still feel compelled to look past that boundary. Our minds are wired for cause and effect, for sequence. When we hear of a beginning, we want to know what came before it, what caused it, what lay waiting in the silence. The truth is that physics doesn't forbid us from asking. It only asks us to redefine what before means. To look for what might exist outside time, we have to imagine conditions where the very concept of sequence breaks down. In that realm, beginnings and endings merge. The boundary of time becomes not a wall, but a horizon, something we can approach but not cross. One of the most well-known ideas about what may have preceded the Big Bang is the quantum vacuum model. In this picture, the universe didn't emerge from absolute nothingness, but from a pre-existing quantum state, a timeless field of potential energy. That field wasn't empty in the usual sense. It contained the fluctuating ingredients of reality in their most primitive form, quantum fields, constantly jittering with uncertainty. Out of those fluctuations, a region of space could spontaneously expand, creating a universe. This idea is supported by quantum mechanics, which allows particles to appear briefly out of empty space, as long as they return their energy quickly enough to preserve balance. If space can give birth to particles, perhaps it can also give birth to universes. In this scenario, the Big Bang wasn't the beginning of everything. It was a local event within a larger timeless reality. The universe we see might be one bubble among countless others, each forming when a quantum fluctuation grows large enough to trigger cosmic inflation. In such a multiverse, before our beginning would simply mean elsewhere. Other universes might have formed earlier or later, though those words lose meaning without a shared timeline. Each bubble universe could have its own arrow of time, its own physics, its own history. From our perspective, they would exist beyond observation, forever unreachable across the inflating space that separates them. The cosmos could be infinite, endlessly generating new beginnings. Another possibility arises from the idea of a cyclic universe. Instead of a single creation event, time might be an eternal sequence of expansions and contractions. In this model, the universe expands until it reaches a certain point, then slows, collapses, and rebounds into a new expansion. Each cycle could erase the memory of the previous one, resetting entropy and starting fresh. If this is true, then our universe may not be the first. It could be one in an endless chain of births and deaths. There's evidence that such cycles could be consistent with known physics. In the framework of general relativity, a universe dominated by gravity could eventually stop expanding and collapse. If conditions were right, that collapse might bounce, triggering a new Big Bang. Quantum gravity might prevent the collapse from reaching a singularity, allowing the transition to occur smoothly. This concept is sometimes called the Big Bounce. It replaces the absolute beginning with an infinite rhythm, a heartbeat of cosmic creation. Some cosmologists have proposed that traces of previous cycles could still be visible in the cosmic microwave background, subtle imprints from before our own expansion began. So far, no clear evidence has been found, but the search continues. If such imprints exist, they could reveal that time extends far beyond the moment we call the beginning. Another approach comes from string theory, where the universe is thought to exist on a higher dimensional membrane, a brain, floating within a larger space. In some versions, multiple brains can collide, releasing energy that triggers a new universe. In that view, the Big Bang wasn't the birth of all existence, but the result of two brains intersecting. Before that collision, both existed in a timeless higher dimensional space. What we perceive as the start of time might simply be the point where those dimensions interacted. In all these theories, the pattern is the same. The universe doesn't arise from absolute nothingness, but from something deeper, something timeless. Whether that something is a quantum field, a cyclic process, or a higher dimensional geometry, it replaces the void with potential. The beginning becomes a transition, not a creation from absence. But what does it mean for something to exist outside time? It's a question that stretches our imagination. Time is the framework that gives meaning to store before and after. So to picture a timeless state requires thinking beyond sequence. In mathematics, it might look like a static equation, all possibilities existing at once, without motion. The universe could emerge from that equation when part of it becomes unstable, transforming potential into actual existence. Stephen Hawking and James Hartley proposed one of the most intriguing versions of this idea. In their no-boundary model, the universe has no singular beginning. Instead, time behaves like a spatial dimension near the origin. Just as the Earth has no edge at its poles, only a smooth curve where north becomes south, time might have no edge at the Big Bang. The universe, in this view, is finite but unbounded. Asking what happened before the Big Bang would be like asking what's north of the North Pole. The question doesn't apply because the geometry changes. In the no-boundary proposal, the early universe can be described by imaginary time, a mathematical construct where time behaves like space. In that regime, the laws of physics are smooth, without singularities. Only when the universe expands and cools does time take on its familiar direction. What we call the beginning would then be a transition from a timeless space-like state to the temporal universe we know. It's possible that timelessness isn't separate from time, but is simply its deeper layer. At the quantum level, the universe may not evolve through time, but exist as a superposition of all possible histories. Each history contributes to the overall state, and time emerges only when one history dominates, when observation, interaction, or entropy creates a direction. From that perspective, before the beginning is not a moment we've lost, but a state that still underlies everything. This concept challenges our intuition, but it also offers a kind of symmetry. The universe might not have started with a single spark, but with a transformation of form. The timeless became temporal, the potential became actual, the possible became real. That transformation could still be happening everywhere, continuously. Every moment we experience as now might be another instance of timelessness becoming time. And while these ideas are grounded in equations and models, they also carry a quiet philosophical depth. If time had no true beginning, then existence itself may be eternal, not in duration, but in presence. The universe, in all its forms and cycles, could be a perpetual process of becoming, without ever having emerged from nothing at all. That notion finds echoes in ancient thought. Long before modern cosmology, philosophers speculated that the universe might be eternal, that beginnings and endings are illusions of perception. In some traditions, creation is seen not as a single event, but as an ongoing unfolding, a continual transition from potential to reality. Modern physics, in its way, returns to that idea, describing a universe that may have always existed in some form, whether as energy, geometry, or probability. If time truly began at the Big Bang, then everything we know, every galaxy, every life, every thought, fits within that 13.8 billion year span. But if there was something before, something timeless, then the story is larger than we can measure. It means that the universe might have roots that stretch into a reality we can never observe directly, but which continues to shape us in ways we don't yet understand. Even the cosmic background radiation, the oldest light we can see, may only hint at what came before. Its uniformity, its slight fluctuations, its faint glow, all could be shadows of an earlier state. We see the after effects of beginnings, but not the beginning itself. Our instruments measure the remnants of transitions, not the source from which they came. What we call the beginning might therefore be a boundary of perception rather than a true origin. Beyond it, the universe could exist in forms that don't require time, in symmetries, equations, or fields where change is meaningless. In that timeless realm, everything that can happen already exists, waiting for conditions that allow it to unfold. This idea doesn't make the beginning less miraculous, it makes it continuous. The birth of the universe may not have been a singular event, but one of many awakenings within a greater ongoing process. Each spark of existence could be part of a cycle without start or end. In that sense, the universe never truly began. It has always been beginning. From this perspective, before isn't a time but a state of possibility, the seedbed of everything that can be. When that possibility becomes unstable, time begins, and once it begins, it carries forward endlessly, branching, evolving, giving rise to structure and consciousness, to questions and curiosity. The fact that we can wonder about what came before time is itself a consequence of that unfolding. So when we ask what existed before the beginning, perhaps the answer isn't something that can be seen or measured. Perhaps the answer is simply that time itself was waiting, not as a ticking clock, but as potential, silent and still, ready to awaken into motion. And in that awakening, everything that would ever exist began to move. That motion has never stopped. The expansion that started then continues now. The energy that filled the first moment still fills the cosmos. The timelessness that may have preceded it still underlies it, woven invisibly into the laws that govern every change. The beginning wasn't the start of time so much as the moment when time learned to express itself. And perhaps, somewhere beyond what we can reach, that process is happening again. Timelessness finding form, silence finding rhythm, nothing becoming something once more. If there was something before the beginning, then perhaps there will also be something after the end. The two ideas feel naturally connected, like reflections of one another. Just as we wonder what preceded the birth of time, we can ask what will follow its conclusion, if it will have a conclusion at all. To imagine the end of the universe is to look into a mirror and see the beginning staring back, transformed but familiar. From the moment the universe began expanding, its fate was tied to a balance between gravity and momentum. Every bit of matter pulled inward, while the expansion pushed outward. For billions of years, these forces contended silently, shaping the cosmos. The outcome depends on how much matter and energy the universe contains, and on the strange pressure of dark energy, the force that drives its accelerating expansion. If gravity is strong enough, the universe could one day halt its expansion and collapse. If not, it will continue to stretch forever. Both possibilities lead to endings that feel like beginnings in disguise. In the first scenario, gravity eventually wins. The expansion slows, stops, and reverses. Galaxies begin to drift back toward one another, drawn by their mutual attraction. Over unimaginable timescales, the universe contracts, growing hotter and denser. The night sky brightens as distant galaxies approach, their light blue shifting instead of red shifting. Stars collide, black holes merge, and the background radiation grows warmer. In this reversal, time itself might seem to compress. Every process that once expanded outward would begin to fold inward. As the universe contracts further, the distances between galaxies shrink, temperatures rise, and matter once again becomes a thick radiant plasma. In its final moments, everything could collapse into a single dense state, not so different from the one that existed at the beginning. That collapse could mark the end of one universe and the birth of another. The Big Bang and the Big Crunch might be two sides of the same process, separated only by direction. In some cosmological models, the laws of physics themselves remain symmetric under time reversal. This means that, in theory, if the universe were to contract perfectly, its equations would describe a mirror image of the expansion, a rewind of cosmic history. Galaxies would unform, stars would unburn, atoms would unbind. From our perspective, it sounds impossible, but mathematically it's elegant. In that mirror, the end and the beginning are identical events viewed from opposite sides of time. This symmetry lies at the heart of many physical laws. The equations governing motion, gravity, and electromagnetism don't inherently distinguish between forward and backward time. A movie of particles bouncing in a box looks the same in reverse. The difference, the reason we feel time move forward, comes from entropy, from the increase of disorder. But if the universe were to collapse completely, the conditions might reset. Entropy could reach a maximum and then somehow begin again. Time could start over, its arrow reversed, its rhythm renewed. That's one version of the mirror, a literal reversal of cosmic flow. But there are others. Some theories suggest that the end of our universe might trigger the birth of a new one, not through collapse, but through transformation. In these models, black holes play a central role. When matter falls into a black hole, it's crushed into an incredibly dense state, similar to the conditions of the Big Bang. Some physicists propose that this compression could create a baby universe on the other side of the event horizon. From within our universe, the black hole looks like an end, a place where time stops. But from within that new universe, it could look like a beginning. This idea blurs the distinction between creation and destruction. Every end might contain the seed of a beginning. The structure of space-time could allow new regions to form within old ones, branching universes emerging from collapsed stars. The cosmos would then be self-replicating, continually generating new beginnings as it ages. The death of one universe would feed the birth of another, endlessly. Even if our universe doesn't collapse, there are other endings that resemble beginnings in quieter ways. If dark energy continues to drive the expansion, space will keep stretching faster and faster. Galaxies will drift apart until their light can no longer reach one another. The stars within each galaxy will burn out, leaving behind black dwarfs, neutron stars, and black holes. The universe will grow darker and colder, entering what physicists call heat death, a state of maximum entropy where no energy remains to fuel change. At first, that might sound like a final stillness, an ending without renewal, but even that stillness has a kind of symmetry. The same equilibrium that defined the early universe, when everything was uniform and featureless, would return. The cosmos would end as it began, smooth, empty, and silent. The arrow of time, driven by entropy, would have completed its journey from order to disorder, from difference to sameness. In that sameness, time might lose meaning once again. Without change, there is no before or after. The end could become another kind of timelessness. Some physicists have suggested that in the far future, quantum fluctuations could once again disturb that stillness. In an infinite time span, tiny irregularities might appear in the vacuum, small pockets where energy briefly gathers. If conditions were right, one of those fluctuations could trigger another big bang. The cycle would begin again, spontaneously. The universe would awaken from its long sleep and start anew. This vision turns the end into a renewal, not by intention, but by probability. If time continues indefinitely, even the most improbable event eventually happens. Given infinite time, beginnings are inevitable. In that sense, the end of our universe might not be an end at all, but part of a larger pattern, a breathing of existence, expansion followed by renewal, each era giving rise to the next. Another way to see the mirror of time's end is through symmetry itself. Many cosmologists suspect that the laws governing the early universe contain time reversal invariants, meaning they would look the same if time ran backward. If that's true, then on the other side of the Big Bang, there could exist another universe moving in the opposite direction of time. In that mirror universe, entropy would increase opposite to ours. From its perspective, we would be the ones moving backward. This idea, sometimes called a CPT symmetric universe, offers a striking picture of cosmic balance. Instead of time starting from nothing, it splits in two, with one branch moving forward and the other backward. The Big Bang becomes not a beginning, but a point of symmetry, a central mirror connecting two opposite flows. The two universes would be identical in structure, but reversed in time, matter, and charge. Each would see the other as existing before its own beginning. If such symmetry exists, it would mean that the universe is fundamentally self-balancing. For every direction of time, there's a counterpart. The arrow of time we experience isn't universal, it's local, tied to our branch of reality. Somewhere, beyond the horizon of our understanding, another branch might unfold in reverse, its future our past, its end our beginning. All these possibilities, the big crunch, the big bounce, the quantum renewal, the mirror universe, share a common thread. They erase the distinction between beginning and end. They suggest that time may be circular, that the universe is self-contained, that creation and destruction are not opposites but phases of the same process. It's a humbling idea. We tend to think of time as linear, with a clear origin and an inevitable destination. But if the universe loops, or mirrors, or regenerates, then time may have no ultimate direction. It could be a closed curve, endlessly folding back upon itself. Every moment could be both cause and effect, every beginning also an ending. Even if the universe's expansion never reverses, the concept of time's mirror holds meaning in another way. On a human scale, the cycles of time already reflect themselves endlessly. Life emerges, grows, and returns to the elements that created it. Stars form, burn, and scatter their remnants to make new stars. Every death feeds another birth. The same atoms that once belonged to ancient stars now form the cells of living beings. The pattern repeats across every scale, from galaxies to organisms. The universe recycles itself continuously, each transformation a new beginning disguised as an ending. On the smallest scales, Even the decay of particles carries the hint of renewal. Quantum fields fluctuate, giving rise to brief appearances of particles that vanish again, contributing to the constant dynamism of existence. In that constant interplay of creation and annihilation, time itself finds balance. When viewed from far enough away, the whole history of the cosmos might resemble a single pulse, an expansion and contraction, a beginning and end unified into one rhythm. If you could step outside time and see the totality of existence at once, perhaps it would look perfectly symmetrical, every moment reflected across its opposite, every motion mirrored by another. From that perspective, there would be no true first or last moment, only continuity, a single, eternal geometry of change. And even if we never find evidence for cycles or symmetry, the idea remains a reminder of how intimately connected beginnings and endings are. The forces that drive creation also drive decay. The conditions that make stars shine also guarantee that they will one day fade. The expansion that allows galaxies to form will eventually scatter them into solitude. The same laws that began the universe will one day bring it to stillness. Yet within that stillness lies the potential for renewal. Whether through collapse, fluctuation, or symmetry, the universe may always find ways to begin again. Every process that ends feeds into another that starts. Every fading light gives way to another rising one. Time, in its full scope, may be less a straight line and more a continuous surface, bending, folding, and turning back upon itself in patterns we can't yet see. If the universe truly mirrors itself, then perhaps we are reflections too. The matter that makes us was once energy in the first stars, and one day it will return to the same cycle, carried by the same forces. The story of existence isn't a march from start to finish, but an ongoing loop of transformation. In that light, the end doesn't erase the beginning, it completes it. The two are inseparable halves of the same structure. The Big Bang and whatever follows it may be one continuous curve in space-time, folding so subtly that neither edge can exist without the other. Time's mirror is not just a metaphor, it's a geometry, one that holds every past and every future within the same vast reflection. And as the universe continues to expand, as galaxies drift and light stretches and stars fade, that reflection remains. The quiet symmetry that has always linked creation and conclusion. Perhaps the end, when it comes, will not feel like an ending at all. It will feel like what the beginning must have felt like, a moment of transformation, a shift in form, a passage from one rhythm of time to another. If the end of time can reflect its beginning, then perhaps time itself has never truly left its origin. The first moment of the universe, that infinitesimal fraction of a second when everything expanded from near nothing, may not have passed in the way we imagine. It may still be unfolding, still present in every change, every motion, every heartbeat. The birth of the cosmos might not be a memory buried in the past, but an event that continues quietly, everywhere, all the time. From the perspective of physics, the expansion of the universe is not something that ended long ago, it's still happening. Every second, the distances between galaxies increase, space itself continues to stretch, and the fabric of reality keeps generating new intervals of existence. The moment of creation never stopped expanding. It simply slowed and cooled, its energy transforming into matter, light, and eventually into everything we can see. The same expansion that began billions of years ago continues now, flowing through the air you breathe and the ground you stand on. When we talk about the age of the universe, roughly 13.8 billion years, we often picture it as a long chain of moments extending from the Big Bang to today. But that chain isn't separate from its first link. The Big Bang wasn't a distant spark that happened and faded. It was the start of a process that still runs beneath everything. Each second you experience is a continuation of that original event, another ripple in the same expansion that began at the beginning of time. The atoms in your body carry that history, They were forged in the centres of stars which formed from the collapse of hydrogen clouds created in the first few minutes after the Big Bang. The oxygen you breathe, the carbon in your cells, the calcium in your bones, all of it was once energy released in that first explosion. When you move your hand, when you take a breath, when you think, the particles involved have been moving through time since the moment the universe began. They've never stopped. They've been part of a continuous unfolding from that original instant of creation. If you could trace those atoms backward, following them through every transformation, you would find no gaps. You would pass through the formation of Earth, the birth of the Sun, the collapse of interstellar clouds, the fusion of hydrogen in ancient stars, the condensation of primordial gas, and eventually the plasma of the early universe. You'd arrive at the same event that gave rise to space and time themselves. Nothing in that chain is separate. The first moment and this moment are connected by an unbroken thread of existence. That connection changes the way we can think about time. Instead of imagining it as a line with a start and a finish, we can think of it as a continuous field, one that began everywhere at once and is still expanding in every direction. The Big Bang didn't happen in one place, it happened everywhere, simultaneously. Every region of space we see today was once part of that original moment. The past is not behind us, but beneath us, layered into the structure of reality. The light that fills the sky at night, the warmth that reaches you from the sun, the faint cosmic background radiation that still glows across the universe. All are remnants of that same beginning. The photons travelling through space today were released long ago, but their journey is not finished. They're still moving, still carrying the energy of creation forward. In that sense, the first light never went out. It only stretched, dimmed, and spread. The universe is still filled with its faint echo, whispering across time. And time itself, as we experience it, may be a local expression of that same expansion. The reason seconds exist, the reason change is possible, is that the universe is still unfolding. Every process, from the orbit of planets to the firing of neurons, is built on that expansion. When you feel time passing, what you're feeling is the continued unfolding of the cosmos, the same movement that began when spacetime first came into being. It's strange to think that we live inside a single event. The Big Bang is not behind us. We are still inside it. Every galaxy, every star, every life is a phase of its expansion. If you could step outside the universe and look back, you wouldn't see a fireball receding into emptiness. You'd see a vast, continuous fabric of space, growing everywhere at once, a living geometry that never stopped expanding. The beginning is still happening, only its form has changed. This view makes time feel less like a sequence and more like a condition. The beginning wasn't a past event, it was the establishment of possibility. The fact that the universe still exists, still changes, still flows, means that the first moment continues in every particle and every force. The universe is the Big Bang, still occurring. The matter that once blazed as pure energy has cooled and organised, but it remains the same energy, still behaving according to the same laws. Even the rhythm of your thoughts depends on that continuity. The chemical reactions in your brain, the flow of blood, the oscillations of your neurons, all are made of matter that began as fluctuations in the quantum fields of the early cosmos. The warmth of your body is the cooled residue of that original energy. When you sense time passing, you're sensing your participation in that same expansion. You're made of it, moved by it, carried forward within it. The more scientists study the universe, the clearer it becomes that nothing within it is separate from its origin. The background radiation that fills space is a map of the first moment imprinted into reality. The distribution of galaxies traces the initial ripples of density that began then. Even the passage of time depends on the way space expands, on the same dynamics that were set in motion at the beginning. Every clock in existence, from the ticking of atoms to the rotation of stars, is part of the same universal motion that started everything. This idea isn't just poetic, it's physical. The expansion of space is measured through the stretching of light from distant galaxies. That stretching is the same process that began when the universe first ignited. There's no dividing line between then and now, only scale and temperature. What was once a universe of plasma is now a universe of stars. What was once a blinding flash is now a faint glow. The transformation is continuous, unbroken, still occurring in the same fabric. Even entropy, the increase of disorder that drives time's arrow, connects us to that first moment. The low entropy of the early universe made evolution and change possible. The reason stars burn, galaxies form, and life emerges is because the universe began in a state of remarkable order. That order is still dissipating. Every process we see is part of that gradual unfolding. In that sense, the beginning never ended. It simply expanded into complexity. The arrow of time is the shadow of that expansion, the trace of the beginning stretching forward into everything that happens. If you look at it this way, the universe doesn't have a distant origin. It's perpetually originating. The Big Bang wasn't a one-time explosion, but an ongoing transformation of potential into reality. Every second that passes is another surface of that same wave spreading through existence. The beginning is not in the past, it's in progress. The universe is still becoming. Even the far future, when the stars fade and the galaxies grow dark, will still be part of that same unfolding. The energy released in those final moments will continue to expand, diffusing through space, carrying the remnants of creation further outward. Time doesn't stop when the visible universe fades. It continues, stretching thinner, quieter, but still moving. The first moment keeps breathing through everything. You can see this continuity reflected in the way the universe creates new structure from old matter. The death of a star seeds the birth of another. The collapse of a cloud gives rise to planets. The same atoms that were forged in supernovae billions of years ago now form the air, water, and living cells around you. The transformation is constant, but the total fabric remains unbroken. The universe keeps rearranging itself, never ending the process that began it. The same can be said for the way time flows through awareness. The thoughts you have right now arise from patterns built over years, which themselves arise from biological processes shaped by the history of life, which emerge from the chemistry of ancient oceans, which formed from the dust of stars. Your perception of the present moment is not separate from cosmic history. It's a continuation of it. You are an extension of the universe's beginning, still unfolding through consciousness. In that way, you're connected directly to the first instant of creation. Every moment you live is the same fabric stretching itself forward. The expansion that began with the birth of space-time continues through you, through the movement of your cells and the rhythm of your breath. You're not an observer watching the universe unfold, you're part of the unfolding itself. The same equations that describe galaxies expanding also describe the flow of time within your life. When you look at the stars, you're seeing light that began its journey long ago, but you're also seeing the present expression of that ancient beginning. The light isn't old in the way we usually think of age. It's timeless in its travel. It's part of a single continuum, still in motion, still revealing the universe to itself. The photons striking your eyes tonight began their paths billions of years ago, but their arrival is not separate from their departure. It's all part of one ongoing event, the moment that never ended. Perhaps that's the true meaning of the universe's expansion. Not just growth in size, but a continual unfolding of potential. The transformation of what could be into what is, everywhere, all at once. Time is that unfolding, space is its canvas, and matter is its expression. The universe didn't begin and then continue. It has always been beginning, every instant renewing the same act of creation in different forms, and if the first moment is still happening, then so is every other. The past isn't gone, It's layered into the structure of the present. The future isn't separate, it's already woven into the possibilities of now. The flow of time isn't a river leaving its source, it's the ongoing pulse of the same source, forever active. The Big Bang didn't vanish into history, it became history itself. That realization doesn't make time smaller, it makes it infinite in depth. Each second is both the latest ripple of the first expansion and a doorway to all that has ever been. The entire history of the universe is contained within this moment, not as memory, but as presence. You are surrounded by the evidence of beginnings, in the light that reaches you, the matter that composes you, the time that carries you. And when you breathe, when you think, when you rest, you're participating in the continuation of that moment, the same creation, the same expansion, the same unfolding that began when the universe first opened its eyes to existence. That moment never ended. It became everything. It became you. And now, as we sit here in this quiet stretch of the universe's unfolding, it's easy to forget that we're part of something still beginning. The same expansion that began the first light continues softly, beneath every heartbeat and every breath. Nothing has truly stopped. Every thought, every sound, every slow turn of the earth is another expression of that first movement. The universe has been beginning for billions of years, and it's still beginning now. Maybe that's what time really is. Not a countdown, not a line from start to finish, but a constant becoming. A rhythm that carries us forward even as we rest, even as we dream. The galaxies still drift outward. The background light still hums. The atoms in your body are still cooling from the earliest fire. You've never left the beginning, you've only learned to move through it. So if your eyes grow heavy now, let them. The same flow that carried stars into being will carry your thoughts into quiet. The universe isn't waiting for anything. It's simply continuing, softly, endlessly, without hurry. Sleep well, traveller of time. You're still part of the first moment, and that moment, the one that never ended, is still unfolding right here, right now, all around you,